All right, putting everything together now, we're going to talk about Taylor series and Maclaurin series. Now, what this is, what this basic idea is all about, is how to represent a function with a power series. Let's go through some of the theory behind this, all right? So, firstly, if a function f has a power series, or let's do it this way, suppose the function f has a power series representation. Well, then a few things are true. The first thing we know, and let's suppose this is at the point C. The first thing we know is true is that f of x would equal a series from n equals 0 to infinity of a sub n x minus c to the n. Do you see where the x minus c is coming from? If this is a power series representation at c, well then we can say, okay, it's going to be x minus c to some power times some sequence of terms, and then we add them all up together. You guys okay with that so far? That is a power series, right? In fact, that's a general form of a power series. Even if c is 0, that's still the power series that represent that. So if we have a function that can be represented by a power series, it's going to look like this somehow. Show of hands if you're all right with that one. That's just all we're saying. It says if f has a power series representation, it's going to look like that. Now, what we're going to state next is this. If this is true, if we have a power series representation, because we have these terms, the sequence of terms where we get our series from, all of these a sub n's are going to be constants, true or false? Which means they act as coefficients, yeah? As n goes from 0 to infinity. Then we're going to have x, basically, x to the 0, x to the 1, x to the 2, x to the 3, x to the n, correct? What that means is that for sure, if this means it makes a power series, we're going to have a whole bunch of terms, right? Wherever we stop is going to be the nth term. Does that make sense to you? That's going to be x to the n. What that means is that the f to the n derivative must exist. It's got to be there. Because what we're going to end up getting is a whole bunch of coefficients. These are constants, fractions, I don't care what they are. It's going to be something times x to the blank power. And that nth power means that you could take a whole bunch of derivatives, couldn't you? Hello? Yes, no?
Yes.
If I had like 3 terms, I could take up to a third derivative, and it's going to be there. It's going to be a constant, actually, is what that's going to be. Just say, okay, bring down the power, subtract 1 from it. That's the first derivative. Bring down the power, subtract 1 from it. That's the second derivative. Bring down the third power, subtract 1 from it. That's the third derivative, and so on. You can do that up to the nth derivative, because there's going to be a power n somewhere in your power series, in your list of terms. Does that make sense? So, then we say, all right, well, then the nth derivative of f exists at c. And the way we would write that is f to the, well not f to the, I'm sorry, the nth derivative of f at c. That's what that says. I'll go through it one more time just so that makes sense to you, and then I'm going to show you what we can do with this thing. This is going to be interesting. This is where we're going to get our Taylor series from. So here's the idea. One more time. If f has a power series representation at c, then this is for sure true. Then f can be represented by a power series. Not a problem. A power series is x to some power. If we have x to some power n, and we list out all of these terms, and we start taking derivatives, then the first derivative is going to exist, and the second one, and the third one, and the fourth one, all the way up into the nth derivative, because what's going to happen is that our first term is going to go to 0. It's a constant. Our second term becomes a constant. Therefore, when I take my next derivative, that term goes to 0. That's going to happen until we get down to our nth derivative. Our nth term ends up turning into a constant at our nth derivative. Does that make sense to you? All the rest of them are going to be something like x minus c to the whatever, the next term after the nth one, n plus 1. That's going to be x minus c to the first, and then to the second, then to the third, then to the fourth. But we can take up to the nth derivative, and it's going to exist somewhere. At c just means, hey, plug in c. Not a problem. Show of hands if you feel okay that this is going to exist. And this is going to make a little bit more sense when we go through the next thing I'm talking about. The next thing I want to find out, and I'm going to write stuff up here, I'm going to erase it in just a minute, this is just to show you what this is. The last thing is, I want to find out what a sub n is in terms of my derivative, in terms of that. And we're going to do it this way. You guys ready for it? So we're going to come up with what a sub n is. The idea is, what I'm trying to do is figure out basically a formula that's based on my function that I can put right here. Because if I can do that, if I can base this on my function, well, then I can start building a power series from a specific function. So here's the idea on this. Oh, you know what? Paper did it separately. Let's start with f of x.
Bless you.
Thank you. Bless you. If f of x has a power series representation, then it's going to be represented by this thing. In general, it's going to be represented by this. Give me the first term of this power series. A sub 0. And it would be this to the 0 would give me 1. It would be a sub 0. Then I would get, what's the next term?
A sub 1. X minus c.
To the plus
A sub 2. X minus c squared.
Plus
A sub 3.
X minus c.
plus blah, 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 all the way down until we get to a sub n, x minus c to the, good. You guys okay with that one? Now, this says we stop at n, but in reality, this thing would keep on going forever, never, 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 because that thing does not end. It goes to infinity. Are you with me so far? So here's the point I was trying to make earlier. Maybe you can see it a little bit better now. Do you understand that if this is my power series representation, it basically acts like a polynomial here. It's going to be x to some power. These are all constants. They're coefficients of whatever x term we have. What that means is, could I take a first derivative? Sure. Could I take a second derivative? Could I take up to an nth derivative?
Yeah.
Absolutely. All that's going to happen is I take a derivative of all these things n times, or whatever n is. 5 times, 7 times, a million times. Who cares? If I have a millionth term, then I can take a millionth derivative. And then I can plug c in. Does that make sense? Now this is going to get kind of interesting for us. Let's start taking derivatives. If I take the first derivative, I'm going to erase that. If I take the first derivative, f prime of x. Help me out with this. What do I get? Remember we did this in the last section? This is why we just did that, is so that you understand that you can take a derivative of a power series. That's why we did it. Because now we're going to use the last idea that we had in the previous section right now. So take a derivative. What happens to a sub 0?
0.
That's gone. What happens to a sub 1, x minus c? What's that become?
A sub 1.
Very good. Plus what?
2 A sub 2.
Oh, good. What why the 2? What are we going to get there?
Chain rule.
So 2 times a sub 2, x minus c.
To the first power.
Very good. Plus
3 A sub 3.
a sub 3, x minus c to the...
Second power.
Now this is the one that I really want to focus on. This one. You see, here's why I want to focus on that. What we got from the nth term. Why I want to focus on that one is because when we get down to the nth derivative, do you understand all these things are ultimately going to go to 0? So they're all going to become constants. So I'm really focused on this guy. So what happens here? Oops. And then we would continue. You all okay with that one? That's the one I want you to focus on to see what happens with this. Okay, let's continue. We're going to do like 4 derivatives, 3 or 4 derivatives. So just to get a really strong pattern here. So let's do f double prime of x. Okay, tell me what happens. Come on, you guys got it. What happens here? What happens here? Really what happens is you bring down the 1, don't you?
Yeah.
You really get 2 times 1. Do you see it? A to the second, I'm sorry, a sub 2, x minus c to the 0, but that's going to go away. So I get 2 times 1 times a sub 2.
2 A sub 2.
Yep. Now I don't want you to simplify it because we're looking for a pattern here. Does that make sense? Looking for a pattern. Okay, next up.
2 times
It's 3, don't give me 6, I don't want 6.
3
With
times-
this stuff, we're really looking for a pattern here. So it's 3 times 2 times a sub 3 x minus c to the
First.
plus. Okay, now remember, this is the one I want to focus on right here. What's going to happen?
N
N.
minus 1.
Good, you'll bring down the n minus 1. Then you multiply by,
X minus C.
minus 2, very good. We okay with that so far? Okay, it's going to keep on going. Let's do, this is the last one that we'll do because the pattern's going to be apparent after this. If we did a third derivative, what happens to this term? Where's it go? That's all a constant. That's gone. Does that make sense?
Mm-hmm.
This one would be
3 times 2
3 times
times
2 times
1.
a sub 3 x minus c to the
0.
0. That's going to go away. That's going to be 1. Are you with me? You sure you're with me? Okay. Plus, blah, blah, blah. Do you notice that what happens is that we're going to end up getting a constant for every single term that we have? Are you with me? So check this out. When we did a first derivative, what I ended with was a sub 1 term as a constant. Are you listening? When I did my second derivative, I ended with my a sub 2 term as a constant. Do you see it? A sub 3 had an x with it. When I did my third derivative, I ended with my a sub 3 term as a constant. My a sub 4 term would have an x to some power. Does that make sense? Okay. Now, let's do our next derivative. What am I going to get from this term as a derivative?
N minus 1 plus 2.
A sub n. Very good. X minus c to the
N minus 3.
plus blah, 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 forever and ever. Now, we're going to make a big jump. We're going to go down here and do the nth derivative. Firstly, does this make sense to you where all these things are coming from? Hello, yes, no, are you
Yes.
sure? We're just doing derivatives, we're doing chain rule, no problem. Derivative inside's always 1, so we got it easy here. What I'm trying to get you to see is the pattern that's taking place. What we saw is that, okay, well, when we wrote this down, we got 2, 1. We got 3, 2, 1. We're going to have 4, 3, 2, 1. We're going to have 5, 4, 3, 2, 1. We're going to have 6, 5, 4, 3, 2, 1. We're going to have n factorial somewhere in this problem. Do you see it? Also, it says right here, we have n. We have n times n minus 1. N times n minus 1 times n minus 2. That's a factorial idea. Start with 7, multiply by 6, multiply by 5, multiply by, start with n, multiply by n minus 1, n minus 2, and all the way down until you get to 1. Are you with me? Also, what's happening, I wanted you to see this. First derivative says a sub 1 is your constant term. Second derivative, a sub 2 is your constant term. Third derivative, a sub 3 is your constant term. Nth derivative, a sub n is your constant term. So ultimately, what we're going to get down to is every term before it is going to go to 0. The a sub 1 term goes to 0, a sub 2 term goes to 0, a sub 3 term goes to 0. A sub n minus 1 term is going to go to 0 if we take the nth derivative. Do you get that? At the nth derivative, what's going to happen here is you've subtracted n minus n. You'll have n minus n there. That would give you the 0. Does that make sense? So we bring it down, we'd have an n. Then we'd have an n minus 1. Then we'd have an n minus 2. Then we'd have multiply all the way down until you get 3, 2, 1, and then you'd have an a sub n. Does that make sense? Are you sure it makes sense? We would have x minus c to the n minus n. And then we'd keep on going. This would be a blah, 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 blah. But I want to talk about this for a bit. I'll try to have this be really stuck in your head, because this is what we're going to get our Taylor series from in just a moment, okay? So bear with me for just a second. If you were to take the nth derivative of a function like this one, if you were to do that, an nth derivative means not the first, not the second, not the third, not the fourth, not the fifth, not the sixth, but do it forever and then go up, not forever, but do it to a certain point n. What's going to happen is that every term with a power less than n, it's a polynomial. That's going to go to 0. Do you get that? Every term is going to go to 0 except for the nth term. At the nth term, you will have done so many derivatives. The first thing you do is the n. Then you multiply by n minus 1. then n minus 2, then n minus 3, all the way down until you get to 1. Does that make sense? Now, the n minus n, that's going to give you 0. What happens to this final little piece here? Where's that go? This goes to 1. Anything to the 0 power is 1. So this is going to be gone. So what we know is that if I take an nth derivative, what's going to happen here is because I'm taking this down every time and saying, hey, one more derivative, I bring down the n minus 2. Hey, look at that. One more derivative, look at this. My next derivative, I bring down to n minus 3. Do you get it? My next derivative, I bring down to n minus 4, n minus 5, all the way until I get to n minus 1. And that would give me my 2, and then my 1, and then I'd have a sub n, but then I'd have x minus c to the 0. Because at my nth derivative, it'd be n minus n. And my n minus n would give me 0. Anything to 0 power gives me 1. This would be my very first term. Show of hands if you feel okay with that. Now this doesn't stop. But when I keep going, every term past this is going to have some bunch of crap, x minus c to some power. That's very unmathematical, but I'm trying to get you the idea here. Does that make sense to you? Are you sure? So my my nth derivative, my very first term is going to be n times all this junk, and then a sub n with no x minus c, but every term after that is going to have an x minus c. Do you understand why this does not have an x minus c?
Yes.
Do you understand what all these ones do?
Mm-hmm.
Anything past the nth term is going to have an x minus 1 to 1 more power. So when I take an nth derivative, I still have a power there that's not 0. Does that make sense? Now, let's write this better. What is all that? Very good. Now, what I care about, what I don't care about. I don't care about f, the nth derivative of f at the x. What I want to do is this, at c. So we're going to make one little jump. If this is true, if the nth derivative of f of x is all this junk, then if I want to find the nth derivative of f at c, let's think about what's going to happen. Please bear in mind, this is why I just asked the question, do you understand that there's no x minus n here, or sorry, x minus, what is that?
C.
C. There's no x minus c here, but every other term is going to have an x minus c. Do you get that?
Yes.
Do you understand that f of c means I plug in c for x? Yeah? So if every one of these terms has an x minus c with it, and I plug in c for my x, what's c minus c?
0.
Everything else is going to go to 0. And the only thing I'm left with is this guy, n factorial times a sub n. And that's it. Did that make sense to you? It's kind of weird, right? But this is the idea. Now, here's what's awesome about this. Can you solve for a sub n?
Mm-hmm.
Very easily. This is where we're going to make the jump, so I hope you caught on to this. If every other term has x minus c, when I plug in c, c minus c is 0. All these things are gone. This does not have any x's at all. It's just a constant. This is the first constant. When I plug in c, everything else is gone except for that constant. This is n factorial. This is still a sub n. Let's solve for a sub n. If I solve for a sub n, I get a sub n equals, let's just divide both sides. F, the nth derivative of f at c divided by n factorial. That, ladies and gentlemen, was what I was looking for over here. Well, what that means is that if I have just solved for the a sub n term, this is really kind of a neat idea. Do you understand that this was all in general, right? I made no specific case about this whatsoever. I said if this has a power series representation, we have this. We can take derivatives of it. No problem. Of course we can. Let's do derivatives. This right here would be the nth derivative of f at x. If I plug in c, which wherever my power series is centered, I can do that. If I plug in c, everything's going to disappear except for this very last term. This very last term. It has a sub n in it. So if I want to solve for a sub n, I just divide. What that means is that what we can do is change this power series becomes this power series. Why don't you tell me? Instead of having a sub n, here what am I going to put? what am I going to put?
C.
The nth derivative of f at c. It's hard to, it looks weird. It's weird to say, but the nth derivative of f at c. The nth derivative of f at c. And then what? Over n factorial. Very good. And then what? Okay, I want to make sure that if there's any questions, I answer them right now. Do y'all see what I'm talking about? Do you see that what this thing becomes, this is the same, okay? What this thing becomes is, if I know this is true, which I just proved it that it is, if I know this is true, instead of a sub n, I can have the nth derivative of f at c divided by n factorial. And that is what goes right there. Show of hands if that one made a little bit of sense to you. Okay. What this is a Taylor series. This right here is the Taylor series. Any questions on this at all? Because I'm going to erase this whole side. You sure? Did it make sense to you? Some basic derivatives. Maybe not so basic. So this series from 0 to infinity of the nth derivative of f at c over n factorial minus n minus sometimes x minus c to the n. Let's look at how this would look, okay? Just like the first few terms. What's the first term? Let's plug. What would you plug in to find the first term? 0. Plug in 0. Okay, so if you plugged in 0,
What is f to the 0?
it's not f to the 0. It's you don't take a derivative of f yet. You don't have it. You take 0 derivatives. That's what that little n means. It means if that was a 1, you take the first derivative. If that was a 2, you take the second derivative. That's a 0, you don't take the derivative. Does that make sense? X minus c to the, what would that become?
0.
That would be 1. All over 0 factorial, 0 factorial, if you don't remember, is defined as 1. So this would simply be f of c. You don't take the derivative of f, you plug in c. That's the very first term here. Does that make sense to you? The next term says, okay, add to it now. Take the first derivative, plug in c. Have x minus c to the first power all over 1 factorial. We don't need that 1 factorial, it's just 1. Does that make sense to you? Are you sure? I'm going to do one more term and see if you can hang with me. Plus, what's the next one? Take 2 derivatives, plug in c, divide by 2 factorial multiplied by x minus c to the... Do you see the pattern? Are you all okay with that pattern for sure, for real? Yes, no?
Yes.
This series, did you guys see that we get a series? Seriously, do you see that we get a series? We get a series here. We get, hey, take the function, plug in c, no problem. Take the first derivative, plug in c. Okay, no problem, multiply by x minus c to the first. Take the second derivative, plug in c, divide by 2 factorial. That's where this is coming from, times x minus c to the second power. That's how your factorial and your power always match up. You keep on going for infinity. This right here, this is called the Taylor series. Now, it's going to be a real pain in the rear, but we're going to go ahead and do the Maclaurin series right now. Okay? It's a lot of work to go from the Taylor series to Maclaurin series. Are you ready to do it? It's going to take us about 30 seconds. Here's the Maclaurin series. If C is 0, that's a Maclaurin series. Super hard.
30 seconds.
But it's a harder one,
It's going to take about 30
There's always a
seconds.
catch.
There's no catch. It's easy. It's not easy. I mean, it's the same thing. Listen, you know how like every square is a rectangle, but not every rectangle is a square?
Yeah.
It's kind of like that, okay? That's analogous to what we're doing here. Every Maclaurin series is inherently a Taylor series. Every Taylor series is not a Maclaurin series? A Maclaurin series is simply a Taylor series with C equals 0. You with me? So if C equals 0, you have yourself a Maclaurin series. If C equals 0, this becomes the Maclaurin series. Are they different? No. You do exactly the same thing, it just C is 0. Well, it makes it a little bit nicer, our notation becomes nicer. So f of x would now become, for a Maclaurin series, a series from n equals 0 to infinity. It would just be this. It'd be the nth derivative. Notice how the n does not become 0. It's the c that becomes 0. So what it becomes is f, the nth derivative of f at what? 0. That's a Maclaurin series. All over n factorial. And then what happens here? X minus
0.
So we just have, do you see how it cleans it up a little bit? A little bit nicer looking? Because you don't have that minus c. You don't have the c, you just have 0, because we're plugging 0. It's going to look exactly the same. It's going to be f of 0. No derivative for the first one. Plus, you take a first derivative at 0 over 1 factorial times x to the first, plus the second derivative at 0 over 2 factorial times x to the second, plus, and then so on and so forth, blah, 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 blah. Okay, quick show of hands if you understand the notation and the verbiage, the idea of the Maclaurin series and the idea of a Taylor series and how they differ. Do you understand how they differ?
Yes.
So on a test, when I ask you for, hey, find the Maclaurin series that represents this function, would you be able to do it? Well, not right now,
Not right now.
but would you understand what I'm talking about?
Yeah.
It's a Taylor series with C equals
0.
Done. Now here's a couple, I'm not going to write these down, but a couple pieces of information that are quite important. Firstly, a function that has a power series representation will be represented by a Taylor series. It will be represented by a Taylor series. The converse is not necessarily true, but we kind of assume it to be true. If we find a Taylor series based on the derivatives of some function, that function that we get from that series usually represents our function very well. We assume that to be true for this case. There are cases where it doesn't, but we assume it to be true for us. Does that make sense? So what that means is that if you get a function and you represent it with a power series, it's going to be a Taylor series. If you find some Taylor series of function that you didn't know, that series that you get usually represents the function, if you base it on the derivatives of the function that you're looking for. That's what I'm trying to say. Can we please do an example to clear all this stuff up?
Yes.
Okay. I'd like to get through at least 2 of them. The first one's really quick, really nice and easy. So here's how your question on a test will most likely look no matter what class you ever take in calculus. This is typically how it looks. So if we have a function like this, and I say, what I want you to do, I want you to find the Taylor series that represents this function at a certain point. Find the Taylor series that represents this function at the point c equals 0. Can you please explain to me another way that I could have worded this that would mean the same thing?
Find the Maclaurin series.
Bam. Do I have to say find the Maclaurin series at c equals 0?
No.
No, I just say find the Maclaurin series, and that would be exactly the same thing as what I just said right here. So if I say find a Taylor series at c equals 0, this means find the Maclaurin series. That's all it means. You okay with that?
Mm-hmm.
I'm going to give you the steps on how to do this. If you follow these steps every time, this is going to make your life a lot easier. So here's the steps. Step number 1. Because our Taylor series are based all on derivatives, what you're looking for here, and it's not that hard to actually do, but it's hard to find the pattern, so I said find the pattern's the hard part, okay? Check it. This part, or rather, where am I at? This part never changes. That's going to be n factorial. This part never changes. That's going to be x minus c to the nth, or x to the nth. No problem, whether you're dealing with Maclaurin or a Taylor series. Okay, all you're looking for is this guy or this guy. That's what you're looking for. Does that make sense? And if you have a c, then it's not just going to be c, it's going to be like centered at 1 or at -3, or whatever you have it at. It's going to be around that 1 point. So you're going to have an actual number. What you're trying to find out is find a pattern that represents the nth derivative of f. So, in order to find a pattern that represents the nth derivative of f at a certain point, like 0 or whatever number I give you, in this case I gave you 0, you need to start with the derivatives. So step number 1 is find several derivatives of your function. Start with several derivatives of your function. So find derivatives of f, and I want you to start looking for a pattern. So I'm going to do that right here, and we're going to do another column right next to it, so leave yourself some space. So we start with the function itself. F of x equals what, please? Now, I think I gave you probably the easiest example in the world right now. Okay? What's the derivative of e to the x? Oh, but wait, what's the next derivative? Okay, but wait a minute. How about the next one? Do it a lot. Okay, typically I do 3 or 4 derivatives. In this case, this is pretty straightforward, so we're not going to do that. But you usually do like 3 or 4 derivatives. What you're looking for is the pattern, so that you can go down to here and say, all right, now I know what the nth derivative of f is. You see, you want a pattern so that you can plug in a number to that. So if you know the nth derivative of x, you can find the nth derivative of c, 0, or 1, or 2, or whatever. Sometimes it's not this easy. I'll give you another way to do it in a minute, but sometimes it is. So you're looking for a pattern on your derivative if you can find one. So what is it? Very good. You guys are geniuses. So, number 1, find a derivative of f and look for a pattern. Number 2, plug in x equals c. It should stick with the same pattern. Sometimes you will definitely find a pattern here, okay? It's going to be apparent to you, but what we're not really looking for this. This is x, the nth derivative at x. I'm looking for at c. So our next step is plug in x equals c. Make sure you find the pattern here. This is the big one. So here's what I do over here. I find f of c. I want f prime of c. I want f double prime of c. Only in our case, we know what our c is. You're always going to know what your c is. What is our c here?
0.
So I don't want just f of c. I'm really looking for f of 0. And f prime of 0, and f double prime of 0, and f triple prime of 0. And ultimately, this is what I want. I want f as an nth derivative of 0. Let's see if we can do this. You see, what we're doing here, we're trying to find a pattern based on n for this thing. So what's up? Hey, what's f of 0 when I plug in 1? What's f prime of 0?
1.
What's f double prime of 0? What's f triple prime of 0? Do you see a pattern here?
Yes.
What's the nth derivative of f at 0?
1.
If it never changes, you're just going to get 1. Show of hands if that makes sense to you. So if you can find a legit pattern for the nth derivative of f of x, all you got to do is plug in 0 to right here. It's going to work for you. Does that make sense to you? Sometimes this is really hard. So besides doing just that, we try to look for a pattern amongst these terms, and we try to work this down and get the nth derivative of f at whatever point we're trying to find. As soon as you find this, everything else is easier. Everything else becomes really, really easy. Are you ready for it to get really, really easy? Are you sure? Okay, so here we go.
Just plug it in.
So if we want to find a Taylor series at c equals 0, that's a Maclaurin series. Then what we know is that our function is going to equal a series that looks like this. It's going to be f as an nth derivative of f at 0 over n factorial x minus c to the n. Okay, by definition, by what we just proved, this is the Maclaurin series. This is a Taylor series at, oh, actually I'm a little wrong.
Just x to the n.
This is the Maclaurin series if I just do x to the n. It's a Taylor series at 0 because when I do 0, I'd have x minus 0 to the n. I would have a 0 for my c. Show of hands feel okay with that one. That is a Maclaurin series. That's a Taylor series at c equals 0. They're the same thing. Now, all we got to do is, did you notice why we only have to find one little piece of information? All we're looking for here is that guy. That's it. This stays the same, that stays the same. It's that guy. So we find our derivatives. Cool. Find a pattern if you can. Sometimes you can't. Find a pattern if you can. Plug in the number c. Find a pattern definitely. This is where you have to do it. Whatever you get as the nth derivative at c, this, whatever this is usually, this is the most basic example I can even think of. It's usually based in terms of n. So base this in terms of n and put it right there. You catch that? So all you do is a little substitution. So this thing changes to you tell me, what's it changed to? What's the nth derivative of f at 0? What is it?
1.
It's always 1. Over what? And then? Perfect. That's exactly right. Exactly. So, step number 1, find derivative. Step number 2, plug in x equals c. Step number 3, as soon as you have this thing, set up your series. Now, step number 4 is where the fun begins. Step number 4, well, hey, does that look like something we have dealt with before in this class? Could you find me the interval of convergence?
Yes.
Ah, does that sound familiar? Did you just do homework on that? Or should you have just done homework on that? Yes.
I really good at that.
Now you go through the ratio test, or the root test, or something that will give you the interval of convergence. You see, what we've just done here is we said, cool, this is awesome. You know what? That function has a power series representation. X equals 0, that's a Maclaurin series. Well, we've just found the Maclaurin series, but you need to tell me where it's good for. The where it's good for is the domain. The where it's good for is the x's that make the series convergent. Remember that a function is only represented by a power series when that power series is convergent, when we actually have a sum. Do you remember talking about that? So we're looking for the interval of convergence, the domain for the x's which make this power series convergent that will represent that function. Did you catch all that? It's in the previous section if you want to review back on the power series idea. So, last little thing, step number 4 is find interval of convergence. That is all the stuff that we've just done. Are you starting to see how this chapter, because before it's like, well, does this even build at all? Are you starting to see now how this builds? Why we did all that junk? We did all the convergence tests because of the endpoints of power series. We did the power series, the ratio test for the power series, and the root test for the power series. We did power series for Taylor series and Maclaurin series, and we did those for approximations by Taylor polynomials, which we can do in the next section. So here's our last thing. Find the interval of convergence. You will, I won't say almost always, you'll oftentimes use the ratio test for this. So I'm going to speed through this really fast. This is not the section on learning the ratio test. This is a section on just using it now. This is not a problem anymore. This is part of our problem. The problem really is right here. As soon as you do this, you've solved the problem. The rest of this old stuff. So we're going to do a ratio test, limit as n approaches infinity, absolute value. This would become, by the way, you can simplify this, make this x to the n over n factorial instead of 1, make it a little easier for yourself. X to the n plus 1 over n plus 1 factorial, all over x to the n over n factorial. So far, so good?
Mm-hmm.
Do you see where all that comes from?
Yes.
It's just our ratio test. Tell me when the ratio test says convergence, when this limit is...
Less than 1.
That's why we're doing this, to find the interval of convergence. So we keep on going. That's a limit. Should I drop the absolute value right now?
No.
Oh, please don't do that. Very good. So we have x to the n plus 1 over n plus 1 factorial. Not a problem. and then n factorial over x to the n. What now?
Simplify.
Let's do it. We're going to do it fast. This is gone. We have n plus 1. This is gone. We have x. That gives us a limit as n approaches infinity of, remember what I told you about this? Collect your n terms, separate off your x term. So your n terms become 1 over n plus 1.
Absolute value of x.
Yeah, that doesn't have to be an absolute value because this n's always going to be positive. We start at 1. But the absolute value of x of that is important. Show of hands feel okay with that so far. Now be careful on this. You got to be really good at this. Be able to determine what this limit's going to be. What is this limit going to be?
0.
All the time?
No.
For anything that you plug in for x, remember x has to be an actual number. Can't be infinity. For anything you plug in for x, is this going to be 0?
Yes.
Yeah, it's something over infinity that gives you 0 times whatever I got. I don't care what that is. This is going to be equal to 0 for all x. For all x. You with me? Now, why is it important that we got a 0 here? Does that help us at all?
It's less than 1.
Ah, this was the ratio test. Since 0 is always less than 1, ratio test. For all x, can you tell me what my interval of convergence is if I can plug in any x and I get 0? 0 is always less than 1, right?
Negative infinity, negative
Good.
infinity.
So if I can plug in anything that says my interval of convergence is any number, this series, listen carefully, this series converges for any x. Do you get that? Anything. We just proved it right there. It's always 0 less than 1 by ratio test. It converges for any x. What that means is that this function is represented by our Maclaurin series for any x. Any x you plug in, I can represent it with this series. So for all x means our interval of convergence would be interval of convergence is negative infinity to infinity. Now if you're wondering why in the world are we doing this, what's the point? Here's the point. What's kind of cool, and here's what we would say by the way. We would say that f of x equals e to the x, here's the point, can be represented by the series, power series, n equals 0 to infinity of x to the n over n factorial. That's just right here. That's what we found. And then you state the interval for which this thing converges, which is the interval for which our power series works for a function. On the interval negative infinity to infinity. That's the appropriate way that you write out your answer. You say, hey, the function that we started with, don't forget what we're doing here. What we're doing here is we're actually representing this function with this series. It says this function can be represented by this series on some given interval. If this had been different, we would have had to check endpoints. Remember checking endpoints? We do all that junk. Now, since it's infinity, since our limit is 0, we get negative infinity to infinity. We don't have to check all that stuff. But here's the point. What you can do now is use this to approximate this. For instance, understand that what this is, what is that? Well, we could actually do it. If I wanted to find f of 2, that would be e to the second power. If I wanted to be as accurate as possible, I didn't need a calculator or whatever. Here's what I could do with that. It's really cool. Notice how I have an e here. Does this have an e in it?
No.
Yet when I do my series, if we did this, if I plugged in 0, I would get x to the 0, so I'd get 2 to the 0 over 0 factorial. I would get 1 plus. I plug in, remember my x is 2 in this case. Are you with me on this? My x would be 2. You know what, maybe it'd be easier if I did this. F of x is 1 plus, if I plugged in 1, I get x to the first, plus if I plugged in 2, I get x squared over 2, then x to the third over 3 factorial, then x to the fourth over 4 factorial. Do I have that right? Can you double check me on that one, make sure I'm good? Am I? Yes, no? Okay. So, if I want f of 2, basically if I want e squared, well, I have 1 plus 2 plus 2 squared over 2 plus 2 to the third over 3 factorial plus 2 to the 4th over 4 factorial. And if I do that forever and add them all up, I will find out exactly what e to the second power is. Is that interesting to you? This doesn't even have an e in it. But when I add them all up, I get e squared. You could do e to the first if you wanted to. You could find out how much e is based on just this polynomial. That's crazy. So if you want a good approximation, do it to the 5th term. Add them all up. You're going to have a pretty darn good approximation for what e to the second is, or e to the first, whatever you want to plug in. If I want e to the first, I just plug in 1. E to the 7th, just plug in 7, and then add them up. And you get as accurate as you want to on that approximation. Show of hands if that one made sense. Kind of cool, right? That's the idea. All right, let's continue our examples on how to find Taylor and Maclaurin series. Now, if you remember from last time, I gave you some steps on how to do this. I want you to read those steps to me. What's the first step in finding a Taylor or Maclaurin series? What should we do first?
Find the derivative of
How many derivatives?
At least 5.
You know what? As many as it takes for you to find a pattern. If you can find a pattern on the first derivative, fine. Like e to the x, so it's really easy. On some of them, you can't do that. So do 3, 4, 5, however many it takes to actually find the pattern, do derivatives. What's the step after that?
Plug
Plug in
in
x
x equals c.
Very good. In our case, x equals, well, c equals 1, that's going to be our c. So we're going to be plugging in 1. And then we find a pattern for that. After that,
Set up your series.
good. And after we set up our series, we're looking for... Very good. It's going to be a function, right? We got to find out the domain of our function. That is the interval for which our series converges, which our power series converges. So, step 1. Let's go ahead and let's find some derivatives. We always start with the function itself, like ln of x. After that, well, we start taking first derivative, second derivative. Hey, everybody, what's the derivative of ln x, please?
1 over x. 1 over x.
Good. Now, I'm going to write that differently because we're going to be looking for a pattern here. So, when I do 1 over x, usually I want x to some power, not 1 over x. So, I'm going to write this instead as...
X minus x to the power of
Yeah, x to the negative 1 power. So, let's write this as x to the negative 1. That's going to make our derivatives a little bit easier as we go down the way, and it's going to make us find a pattern pretty quickly. Are you with me?
Yeah.
Okay, so we're going to go fast through this stuff. Hang on to your hats here. What's the second derivative, please?
Negative x negative 2.
Okay, I'm going to write negative 1 x to the negative 2. Is that okay with you?
Yeah.
And here's why we're going to do that. When you're doing this, when you're doing your derivatives, do not do things like this. When you do a third derivative, I don't want you to multiply the negative 1 times the negative 2 and get 2. I want you to look for a pattern. Yeah, a negative times negative is a positive, but really we're going to get 2 times 1, x to the negative 3. Does that make sense to you? Are you with me? Remember, you're looking for patterns here. You're looking to make a pattern out of this guy. Not to get the number, to get a pattern. Let's do a fourth derivative and a fifth derivative, and then we'll find it. So the fourth derivative of x, we write a little 4 up there. What's going to happen? It's going to be negative, very good. And it's going to be 3 times 2 times 1 times x to the negative 4. Does that make sense to you?
Yeah.
Do you see what's happening?
Yeah.
Had I put 1, 1, 2, 6, you would not have seen a pattern here. Does that make sense? So when you're doing this, don't do that. Don't do 1, 1, 2, 6, 20, whatever you're getting, okay? So let's do one more. The fifth derivative of x, we're going to get, is it positive or negative?
Positive.
So we're going to get positive, and then 4 times 3 times 2 times 1 times x to the negative.
Yeah.
Very good. Do you see your pattern?
Yes.
Tell me something about your pattern right now, as far as the sign goes. Also, do you notice something? Our pattern does not start with our first term. This is not part of our pattern. This doesn't even work with it. It has no exponent at all. So we can start our pattern after the first term. So after this would be like the 0th term, at the next term. So we don't have to start it here. We notice our pattern goes, okay, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. That's going to be something in it. It's going to be alternating. Do you guys see the alternating I'm talking about? Secondly, tell me something about my exponent. Decreases by 1, that's right. So it's negative, if you want to see the absolute value, increases, sure. So negative 1, negative 2, negative 3, negative 4, negative 5. Tell me how it relates to the derivative that we are taking. To the derivative that we're taking.
Oh, no, it's the same as the
3 negative 3, 4, negative 4, 5, negative 5. The same one, next one will be 6, negative 6. Does that make sense?
Yes.
Okay, tell me something about the coefficient of my x's. What's it doing? It's a factorial, that's right. Now, is it n factorial? Is it the power factorial? Is this 4, 3, 2, 1? Oh, yeah, it's n minus 1. That's right. So it's really close, but it's still a factorial, but it's 1 less than the power we have. Does that make sense?
Yeah.
Let's check it out. If I omit the negatives and positives, this is 2 minus 1 factorial? Sure. Is this 3 minus 1 factorial? Is this 4 minus 1 factorial? And 5 minus 1 factorial? And 1 minus 1 factorial? 0 factorial? Yeah. 0 factorial is 1. Okay, so we could do the nth derivative right now. What we know is that it's alternating. Yeah, it's alternating. It says it's going to be negative 1 to some power. We just got to make sure it starts correctly for us. So we're going to have n or n minus 1 up here somewhere. We'll deal with that in just a second, okay? Next up, well, we're going to have, how do I represent this?
N minus 1 factorial.
Okay, so if I get rid of all the negatives, say I don't even care about those, we're going to have an n minus 1 factorial for sure, and then x to the negative n power. Does that make sense to you?
Yeah.
You sure? Okay, now, this part's what I'm worried about. How can I represent, because right here goes positive, positive, so let's forget about this one. Let's look just here. So I don't want positive, positive, negative, positive, positive. That doesn't really work for us. That's not our pattern. So our pattern doesn't really start until our first derivative term. So omit that. How can I make it positive, negative, positive, negative, positive, negative? How can I start that off? Is it negative 1 to the n or negative 1 to the n minus 1? If I start at n equals 1. N minus 1. That's right. And you know what? If you're not good at it, you go, man, I don't know. Well, if you can't find a pattern here, that's okay. What you're really looking for is step number 2, plug in the numbers. Here's f of, I'm sorry, what are we plugging in even?
1.
Plug in 1. Okay, so f of 1, and f prime of 1, and f double prime of 1, and plug them all in for 1. It's got to follow the same pattern. So it's got to be alternating. It's still going to have a factorial somewhere in there. That's why we did this, is to look for the pattern and make sure it's still the same. Okay, so check it out. F of 1 is, what is it?
0.
Good, because if I plug in 1, I get 0. Now, we just determined that's not going to be part of our pattern, so we're going to be omitting that term. How about this one? 1. How about the next one?
Negative.
How about the next one?
Negative, or 2.
If I plug in,
Oh, no, half. Wait.
plug in 1, you're going to get 2 times 1. Plug in 1, you're going to get negative 3 times 2 times 1. Plug in 1, you're going to get positive 4 times 3 times 2 times 1. Do you guys see that all we're getting here is this series of numbers that are being multiplied together? We don't have any more x's because 1 to any power is still 1. So basically, if you just omit your x's, this is what we get. This happens to be 0 factorial. This happens to be negative 1 factorial. This is positive 2 factorial. This is negative 3 factorial. This is positive 4 factorial. Are you with me still? Is it still alternating?
Yes.
Does it still have a factorial? Yeah, in fact, this is going to be negative 1 to the n minus 1, and then n minus 1 factorial. You can see something here as well. Check this out. If you're good enough to find a pattern, which some of you are, and some of you maybe are going to struggle with this, this is kind of hard to do in general. If you follow the steps I've given you, try not to get just the numbers, try to find your pattern. This becomes a lot easier, okay? But look at this. If I take my x equals 1, like that's my c, okay? Take my x equals c, which in this case is 1, and I plug it in. Do you see that if I plug in 1 here, I get exactly what we found over here? Hello, do you see that? It's got to be the same. So if I plug in 1, I'm still going to get the same thing if I found my pattern correctly. Now, if that's our nth power of f at 1, then here's what we're looking for. What we know is that a Taylor series must look like this. Our Taylor series has to be n equals, in this case, listen, in this case we're not going to start the 0 term. Are you listening? We're not going to start the 0 term, because if I start the 0 term, that's this guy, and that's not following our pattern. So we're going to change to n equals 1. You're going to see another reason why in just a minute. So we're not going to start at 0. We're going to start at 1 because our pattern doesn't start till our n equals 1. Does that make sense to you? Not n equals 0, not the 0 derivative, not the function itself, but at n equals 1. So 1 to infinity. We've got to look like, okay, the nth derivative at, remember Taylor series? At c. What's our c right now?
1.
Okay, and then, say what?
Times x minus c to the n.
X minus, okay, x minus c, very good. X minus
1.
1.
to the
N.
over?
N factorial.
Perfect. Show of hands feel okay with that so far. So we found our derivatives, we actually found a pattern to it. If you find a pattern, if you find the nth derivative of f at x, then all you need to do is plug in your center. If it's 0, plug in 0. If it's 1, plug in 1. And you automatically get the nth derivative of f at 1 if you simply plug in 1. That's literally what this means. Now, I've given you both these steps because if you can't do this, if you can't find the pattern, sometimes you'll be able to find a pattern just from plugging in the number. This is really what we're looking for anyway. So if you can't find the pattern here, use this to plug in your numbers and then find a pattern from these numbers. Show of hands feel okay with that idea. Once you do that, understand that what we're trying to do here is do a Taylor series, or a Maclaurin if we're centered at 0. Taylor series are always nth derivative of f at your point C, at your center. Well, that would be at 1. Hey, we already found that. Then it's x minus your center, x minus 1 to the nth power over n factorial. We proved it last time. So all we got to do now is, well, what? Let's make a substitution. So our Taylor series, therefore, is going to be n equals 1 to infinity. I know I'm going to have an x minus 1 to the n over n factorial. Can you please tell me what goes here? Have I lost you?
No.
What goes there then?
Negative 1 to the power n minus 1 times n minus 1 factorial.
Perfect. That's exactly right. It's literally this thing. If the nth derivative of f evaluated at 1 is this, which we found it 2 different ways, really, then we're going to plug that in. So negative 1 to the n minus 1 times n minus 1 factorial. Okay, I really do need to make sure that you're okay with this so far. I don't think I'm going to give you any sort of recap. I've done it a couple times here. Derivatives, find a pattern. Plug in numbers, find a pattern. This is what you're looking for. The reason why you're looking for this, evaluated at this point, is because that is what a Taylor polynomial is all about. It says find your nth derivative, evaluated at whatever your c is equal to. We have that. Make your substitution. These guys are always the same. It's x minus your center, x minus your c, evaluate at to some power n over n factorial. Do you really feel okay getting that far? Now, before you go any farther, simplify it if you can. For instance, I've got an n minus 1 factorial over an n. I should be able to simplify that. Can you simplify n minus 1 factorial over n factorial?
You're left with n minus 1.
Yeah.
You're not left with n minus 1.
And at the
You're
bottom.
left with n.
What?
N factorial is n times n minus 1 times n minus 2 times all the way down to 3, 2, 1. Are you with me? Look at this. What's that?
Factorial and minus.
N minus 1 factorial. So n factorial is bigger than n minus 1 factorial by one term, by multiplication by n. Does that make sense to you? So don't jump the gun and go n minus 1. No, this is less than that. If this would have been n plus 1, then yes, n plus 1 would be up here. But it's not. This is n minus 1 factorial. This is n minus 1 factorial times n. Therefore, this gets simplified with all this, and we get 1 over n. That's what we get. So this goes boom, boom, n. So our Taylor series becomes 1 to infinity of -1 to the n minus 1 times x minus 1 to the n all over n. That's what we really want to work with. That's going to be nicer than working with this thing for us for sure. Are we okay with that one?
Yes.
You sure? Okay, so we've done derivatives, got it, step 1. We've done plug in the numbers, step 2. We found a pattern, we've made our Taylor series. This is what we wanted to do. This was step number 3. Now step number 4, are we done with this? You got to tell me where this thing converges. So what's the next step? Interval of convergence, very good. How, right side people, how are we going to do the interval of convergence? What would you use here? Absolutely the ratio test. For sure, it's got, well, it had a factorial, but it's got a power of n and something that doesn't have a power of n. You're not going to want to do a root test here. Do a ratio test. Also, ratio test gives us a nice interval here. If we know that the limit is less than 1, we have convergence. Do the ratio test for me right now, please. Oh, by the way, one more reason why you can't start at n equals 0 here. Let me have your eyes on the board real fast. If you started at n equals 0, what's wrong with this picture? The undefined. You couldn't even do it, all right? So we start at n equals 1, firstly because the pattern doesn't even start till the first derivative, n equals 1 derivative, and also for the definition of having a defined series here, you can't even start at 0. Okay, so continue your ratio test. I'm going to go on the board here real quick, so we're going to do the ratio test. But I definitely want you to do it on your own, please. We should be pretty much pros at doing the ratio test. I want to make sure you get the same thing I got. So can I have your eyes on the board here real quick? How many people did the a sub n plus 1 term here and got this, and over a sub n term here and got that? Show of hands if you got exactly that. Cool. What's the next step? What should you do? Simplify as much as you can. What's going to happen to my negative 1s? They gone. So we're going to get a limit. N approaches infinity. Do we get rid of the absolute value, ladies and gentlemen? No, we really don't do that when we have x's in here. We are going to multiply by the reciprocal of our main denominator. So here we're going to have our, this piece gone, still have this piece. Still have this piece. Then we're going to, well, this piece is gone, absolute value takes care of that for us. Multiply by reciprocal, we have n over x minus 1 to the n. What's the next thing that we can do here? Can we simplify? We're going to simplify it, then we're going to collect our n terms and collect the remaining x term. Everything else should simplify here. So, what do we get?
You're going to get n times x minus 1.
Okay, I'm going to get an n. I like that. I'm going to get a limit. N approaches infinity of n over n plus 1. I'm going to get an absolute value. Very good. Why can't I pull out the n over n plus 1 and not have an absolute value? Tell me, explain to me why I can do that. Very good. N over n plus 1 is always positive. We start at 1, we go to infinity. So this is always positive. We collect our n terms, no absolute value, maybe parentheses if you really want to be technical about that, put parentheses around it. What's going to be inside of our absolute value?
X minus 1.
Under 1 or over 1? Where is the x minus 1? On the numerator?
It's going to be on
Very good, because this simplifies all of this. That little plus 1, that says that you have 1 power of x minus 1 more than you had here. Therefore, our x minus 1 is still on a numerator. Absolute value is a little bit big here. So we get our n over n plus 1, no problem. Collect our n terms. We simplify, we get x minus 1, still an absolute value. Now, what do we do? Take a limit, very good. What's the limit of n over n plus 1?
1.
Very good. So this thing is equal to absolute value of x minus 1. Now, tell me something about the test we use. What test did we use? What's that tell us about convergence of a series? So whatever we have here must be less than 1 for convergence. You with me?
Yes.
That gives us our interval. That's great. So right now we know that this series is going to converge when the absolute value of x minus 1 is less than 1. That's when we know this is going to converge. That's when we know that this Taylor series will represent our function ln of x. You with me? That's when we know, because it only works if the series is going to converge. That's the only time we get an output for our function, which is the only time we can actually get a function here. Now, from here, can you tell me my radius of convergence? What is it? As soon as you find whatever's being raised to the nth power right here, as soon as you find that in your absolute value, that right there is your radius of convergence. So the r is 1. Now let's go ahead and do the interval of convergence. From here, what we know by the definition of the absolute value inequality is that -1 must be less than x minus 1 must be less than 1. Do you follow me on that one? That's what a definition of absolute value inequality is. Now we're looking for the interval, so we don't stop here. We want to get x by itself. So when we get x by itself, we have to add 1 to all 3 of our zones, that practically. We get 0 is less than x is less than 2. You okay with that? So notice it. Is 1 in the center of our interval?
Yes.
Right in the center. It's supposed to be there. Is the radius still 1? Can I add 1 and subtract 1 to get these two numbers?
Yeah.
That's why we get our radius here first, and then we get our interval. Now, here's the issue. What about 0 and 2?
Endpoints.
We've got to check our endpoints. Check your endpoint. Actually, you know what? We'll do it together. I want to be a little bit quicker about this. Let's check our endpoints. Any questions on the pattern at all? So this was just to find our pattern, basically just to find this piece right there. Everything else we already know. So here we go. Here's our endpoints. What are our endpoints right now?
0 to 2.
So 0. If my original Taylor series goes from 1 to infinity of -1 to the n minus 1, x minus 1 to the n over n. And I say, I want to plug, what number am I plugging in?
0.
And where am I substituting that for?
X.
So this becomes the series n equals 1 to infinity, -1 to the n minus 1 times
-1
what?
to the n.
Oh, -1 to the n, that's right. Over n. You all okay with where that's coming from?
Mm-hmm.
If you plug in 0 for x, you're going to get 0 minus, oh, that's -1. -1 to the n. Here we got our first little piece, -1 to the n minus 1. We got the second little piece, when we plug in 0 for x, we get -1 to the n. Now, simplify this before you try to do any tests on it. The -1 to the n minus 1 times -1 to the n does not look very good right now. So what we're going to do is, because we have these common bases being multiplied together, what are you supposed to do with your exponents when you have common bases being multiplied together? You add them. So this becomes series n equals 1 to infinity of what over n? I'll tell you it's going to be -1. -1 to the 2n minus 1. 2n minus 1. Okay, show of hands if you feel okay with that one. Now we're going to consider this for a second. What does 2n minus 1 always give you? Plug in n's. What's it always give you?
Odd number.
Gives you odd numbers. It's very good. So we're starting at 1, right? So you plug in 1, we get 2 minus 1, that's 1. Then you plug in 2, we get 4 minus 1, that's 3. Plug in 3, we get 6 minus 1, that's 5. We get odd numbers. The expression 2n minus 1, this gives you odd numbers. Now, how much is -1 to the 2n minus 1 then? What is it?
Always negative.
It's always negative. Very good. Because it's always going to be to the first, third, fifth, seventh, ninth, whatever, always odd. Then -1 to the 2n minus 1. You know what, guys? This is just equal to -1. That's all it is. Does that make sense to you? Because it's always going to be -1 to an odd number. -1 to an odd number is always going to give you -1. Therefore, this series becomes... How much is this whole piece? Do you understand why?
Yes.
If this is always odds, this whole piece becomes -1 over n. You sure you're okay with it? Now, do you remember that we can pull constants out of our series. Negative sum from 1 to infinity of 1 over n. Oh my gosh, we finally have it. Tell me something about the sum from 1 to infinity of 1 over n. What is that?
Harmonic.
That's harmonic, or it's a p-series with p equals 1. Either way you say this, what happens to this series? I don't care about the negative. What happens to this series?
Divergence.
Negative divergence is still divergence, so this thing diverges. So harmonic, therefore divergent. Tell me something about the endpoint of 0. Is that going to be included in my interval of convergence?
No.
Therefore, is that going to be in the domain of my function, as represented by my Taylor series?
No.
No.
It's not going to be my domain. Okay. The next endpoint we got to check is the 2. So let's plug in the 2. If we plug in 2, this series goes from 1 to infinity of negative 1 to the n minus 1. If I plug in 2, how much do I get?
1.
Yeah. 2 minus 1 gives you 1 to the n all over n. Now this one's going to be much more straightforward. We're not going to have any fancy pants math to do up here, okay? How much is 1 to the n? That's easier. I guess this wasn't too hard anyway. You just got another 2n minus 1 is odd numbers. So this becomes negative 1 to the n minus 1 all over n. This whole thing is 1. 1 to the n is always just 1. 1 times anything gives you the anything. Hey, tell me about this series. What do you know about it? It's alternating. It's alternating harmonic. What do you know about the alternating harmonic series? Could you do a different test to show that if you forgot it? Do alternating series test. You got it. Don't do absolute convergence, because this does not converge absolutely. If you do absolute convergence, you get harmonic, and that says divergent. It says not absolutely convergent. It's conditionally convergent by the alternating series test. So this is the alternating harmonic series. By the alternating series test, this thing converges. You state all these things, you tell me what it is, you tell me what you're using to find out convergence or divergence. Say harmonic, hey, divergent, no problem. Alternating harmonic series, I know that's convergent already, or by alternating series test, it converges. So, here's what we know. We know that the function f of x equals ln x can be represented by the Taylor series, and then you show the Taylor series. You say it's negative 1 to the n minus 1, x minus 1 to the n all over n factorial. You show me what the Taylor series is. You say, hey, look at this. This is what we're doing here, folks. Don't lose track of what we're doing. Don't just miss the forest for the trees and go through this process and don't understand what we're doing. What we're saying is this. You ready? This function is represented by the Taylor series right here, centered around 1. On the interval, and then you tell me what the domain of this function is. Question.
Now, do we need the n minus 1 factorial one?
Sorry, it should be n.
Okay. You want
Just
to
n.
simplify it?
It's this.
If you want to simplify it, you can put it.
The simplified form. So let me make sure I got it right. We got negative 1 to n minus 1, x minus 1 to n all over n. Yeah, give me this. Give me the simplified form. This is the easiest one, okay? You're not going to do this if you can do this and get the same numbers. So do this. So our function can be represented by our Taylor series, we got it right here, but only on the given interval that you just found. This is the only time that this series will converge. Therefore, it's the only time that this series will represent this function. It's on what interval?
Parentheses 0 to 2 bracket.
Bracket.
Good. So parentheses because 0 is not included, bracket because 2 is. That means you can plug in any number from 0, non-inclusive, up to 2, inclusive, and what you plug in is going to represent that function if you do this series to infinity. Show of hands if you understand that one. Okay, cool. Tell you what, I'm going to show you a couple other problems, as many as I can do to get you really good at this. Because there's some other techniques that you're going to have to learn here in order to be successful at doing your Taylor series and the Maclaurin series. Okay, last chance for any questions. Do you have any? I want to start fresh. Do you have any questions on this one? Have I explained it well enough for you all to understand it? Cool. So our next example write down f of x equals sine x. Yes, we're going to do trigonometric Taylor series. Don't pee your pants, it's fine. And what I want to do right now, I want to find the Maclaurin series. What's that mean?
Take the
C
derivative.
equals 0.
Zero.
Find the Taylor series.
That's
C
right.
equals 0.
Maclaurin series is a Taylor series with C equals to 0. Not a problem. So what we're looking for ultimately is this. What we want, what we know is we want a series that has the nth derivative at 0, x to the n over n factorial. Does that make sense to you? Hello, yes, no?
Yeah.
That's a Taylor series, right? It just so happens that C would be 0, making it a Maclaurin series. That's what our goal is to find that thing. Now, where do we start?
Find F.
Say what now?
Find F and
The nth derivative of f. That's hard to say. The nth derivative of f. That's what we want. So we start doing derivatives. That's step number 1. So, okay, we'll start with our function. Our function sine x. What's our first derivative, please?
Cosine of x.
What's our second? Oh, come on. I know that more than one of you know this.
Negative sine of x.
What's our third derivative?
Negative cosine cosine x.
What's our fourth derivative?
Sine of x.
Is there a need to go any further?
No.
Okay, I hope not. Sine, cosine, negative cosine. Sine, cosine, negative cosine. Sine, cosine. Here's the problem. Oops. What's this? What is that?
question mark.
Because I don't know. Because it depends on where you stop, doesn't it? It depends on whether you stop on a remainder of when you divide your derivative by 4. If you divide it by 4 and it's 0, cool. 1, 2, 3, 0, 1, 2, 3, 0. It's going to be a cyclical pattern. It's like number theory, okay? So, yeah, you don't know what that's going to be. So this one, we can't do it this way. Sometimes we can't find an nth derivative of f explicitly because it's going to depend on what remainder of 4 that we're in on our cycle. Well, you can even see it clear here, number 2. Step number 2 says, okay, start plugging in. Oh, I'm sorry, what number are we supposed to plug in here?
0.
Very good, our C is 0. And the first derivative at 0, and the second derivative at 0, and so forth. And so on. Let's see if you can give this a try. What's the function itself at 0? Yep. What's the first derivative at 0?
1.
And then?
0.
And then?
8.
And then?
0.
So we go, this is weird. 0, 1, 0, negative 1. 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 What is the nth derivative at 0? Again, I don't know. It's one of these 3 choices. It's either 0, 1, or negative 1, but I don't know what it is. We're going to have to go a different way around this, all right? So when you come up with this and you can't find a pattern, start listing out the terms of your Maclaurin series or your Taylor series. Start listing them out. So we're going to start there. So if we really list this out, our Maclaurin series we'll do it over here. Our Maclaurin series. What's our very first term? Well, this would say that you start at 0, right? You'd have x to the 0, that's 1, over 0 factorial, that's 1. You'd take 0 derivatives. That's basically just f of 0. Remember doing this like the first day we did our Maclaurin or our Taylor series? We started listing out the terms for it. You'd start off with f of 0. Do you follow me? Taylor would be f of c, no problem. Then we go, okay, cool, we'd add to it the first derivative at 0 times x to the first, all over 1 factorial. That would simply be 1. Be okay with that one? Then we'd have the second derivative at 0. We would have x squared over 2 factorial. No problem. Then we'd have the third derivative at 0. We'd have x to the third all over 3 factorial. Then we'd have the fourth derivative at 0, x to the fourth power all over 4 factorial, and we would not stop. I want a show of hands if you can get from here to here. You understand what I'm doing. Show of hands if you do that. Okay. So our yes, no? Our Maclaurin series says when you plug in 0, you get no derivatives. Bam. No derivatives. At 0. X to the 0 is 1. 0 factorial is 1. Then you plug in 1. So our first n equals 0 term, n equals 1 term. Plug in 1. You get a first derivative. No problem. X to the first all over 1 factorial. Plug in now 2. You get a second derivative. You get x to the second all over 2 factorial. Now plug in 3. You get a third derivative. X to the third all over 3 factorial. You plug in 4. Fourth derivative of 0. X to the fourth over 4 factorial. Are you paying attention?
Yes.
Does it make sense to you? Let's plug in the numbers. What's f of 0?
0.
What's f prime of 0? 1 times x is x. Does that make sense? Watch carefully. What's the second derivative at 0?
0.
This is why we did this. So this whole thing becomes 0. What's the third derivative? What's the fourth derivative? 0. Do you guys see what I'm talking about? Are you with me at all? I don't want to lose you here, but I want you to be with me, but I got to move too. So do you get that the function at 0 is 0? Yes, no? The first derivative at 0 is 1. The second derivative at 0 is 0. Third derivative at 0 is negative 1. Fourth derivative at 0 is 0 times anything is 0. Plus, how about the fifth derivative? Is it going to be 0 or 1 or negative 1?
1.
It's going to be 1. 0, 1. 0, negative 1. 0, 1. 0, negative 1. 0, 1, 0, negative 1, 0, 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. It's like a song. Having fun, right? It's cool. Well, now let's simplify this a little bit. Do I really need to include all my zeros?
No.
Now, we come to a fine point that maybe it makes a difference, maybe it doesn't. I like to think that it does, okay? We're going to come to a fine point. This really is the first term. Second term, third term, fourth term, fifth term. We're going to redefine our series here, because what's going to happen is if I omit my first and my third, my 0th and my second term and my when n equals 3 and 2 and 4, I'm going to get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus blah, 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 forever and ever and ever and ever. Can you quick show of hands if that makes sense to you? Now, if I try to define this as a series in terms of n, my n's are going to compete. For instance, my n's are stemming from here, aren't they? Are you with me? Which means that this is going to be my 0th, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th. But this I want to consider my 1st, 2nd, 3rd, 4th. So can I define a series in terms of n? Yes, but understand it's a different n. It's a different series. So what I'm going to do right now, I'm going to use the letter k, so we have no ambiguities of what's going on, okay? We're going to define this thing right here as a different series. So tell me, on this series, from k equals 1 to infinity, tell me what's going on. Tell me something about that you guys see. It's alternating. Okay, that's easy. Let's start with that. Negative 1 to the, is the first term positive? Or is the first term,
Positive.
oh, you know what, let's start at 0, actually. Start at 0, just to keep our Maclaurin series in mind here. Start at 0. First term positive, first term negative.
Positive.
So the only way that we're going to do that is if we do,
And
K minus 1.
oh, which one?
K.
N minus 1 would give us 0, and that'd be negative 1.
K. Just K.
It'd just be k. Because if I do negative 1 to the 0, I get positive 1. Does that make sense? If I do negative 1 to the first, I get negative. Second, I get positive. Third, I get negative. This is going to work for us. That's where we're getting our alternating from, is negative 1 to the k. Are you sure you're okay with it?
A-OK.
A-okay. Okay. You get an A because you're okay. Not a problem. Now, multiply. Tell me what our x's are doing. What are the powers of x doing?
Odds.
They're odds. Hey, we just dealt with odds.
2k minus 1.
We just dealt with odds. Well, let's see if that works. If I plug in 0, wait a minute. I'm going to get negative. Is this x to the negative 1 power? How can I change that to make it work?
Plus 1.
That'll work. That'll work. So if I do 0, okay, what's 2 times 0?
0.
Plus 1?
1.
Let's do, plug in 1 now. Plug in 1. So remember, 0 should give me my very first technical term. If I plug in 1, it should give me this term. Are you with me? Plug in 2, it should give me this term. That's why we redefined our k's so we don't get ambiguous with that. So plug in 1. 2 times 1 is? Plus 1? Hey, let's plug in 2. 2 times 2 is?
4.
Plus 1?
5.
Boom. Now, what's the denominator doing?
2K plus 1.
It's exactly the same, but with a factorial. You better make sure this is accurate before we go any further, okay? So, we start off, derivatives are really easy. Our pattern is really easy, but there's no way for us to explicitly define it, because we don't know what this is going to be, the nth derivative of f. I don't know. It's supposed to be a little n, by the way. I don't know what that's going to be. So we write out the terms. Maclaurin series says, you know what? You're going to have f is 0. F prime is 0 times x. F double prime is 0. X to the second over 2 factorial. X triple prime of 0. X to the third over 3 factorial. And so forth and so on. Except with our pattern that we just found, we know we're going to go coefficients-wise. 0, 1, 0, negative 1. 0, 1, 0, negative 1. That's going to basically omit half our terms. They're all gone. So we just take the terms that actually have something, and what that does is that takes a series with like 2 n terms and gives us a series with n terms. Or practically, we have a series with n terms and we get a series with n divided by 2 terms, or k terms, where k equals n divided by 2. Well, if that's the case, let's redefine it so we don't get confused on the terms themselves. We say, okay, let's start k equals to 0 and go to 1, or go to infinity. Then we have, what's that say? What's this part say for your series?
Alternating.
It's alternating. So this says we're alternating, no problem. This says we're taking x to the odd powers over odd numbers factorial. This is our Maclaurin series. Now, what are we going to do with our Maclaurin series? Say it again?
Ratio.
Definitely ratio test. It's got a factorial in it, right? We're not done here. You see, what we've done is we've defined, we know that f of x equals sine can be defined by this Maclaurin series. It can be defined by it. But we got to have the interval of convergence, so do the ratio test. Notice we're in k's, so your limit should go from
K.
k approaches, not n, but k approaches infinity. So go for it. This one should be quite easy for us. The simplification is going to be a little bit crazy, but too hard. Oh my gosh. Negative 1 to the k plus 1 times x to the, you know what? If we do k plus 1 here, do you see that's going to be 2 times k plus 1 plus 1? Do you see that? 2 times k plus 1 plus 1.
Plus 2.
Okay, and this is going to be, same thing, 2k plus 1 plus 1 factorial. Sounds like we have a stutter, doesn't it? Plus 1 plus 1? No. Negative 1 to the k, x to the 2k plus 1 all over 2k plus 1 factorial. No problem. But I want to make sure you guys have exactly the same thing that I have. Here, show of hands if you do have exactly that thing. Is the ratio test getting pretty easy for you?
Yes.
It should be, right? We've done it like 50 million times. What's going to happen to my negative 1s?
Cancel. I mean, they
They gone.
don't matter.
Absolute value takes care of our negative 1 to any power. Now, of course, we have a complex fraction. We'll write this as a limit. Don't change your k to an n. Absolute value, don't lose that. On our main numerator, let's distribute. Notice this, you're going to have 2k plus 2 plus 1. That's 2k plus 3. Do you guys get that one? X to the 2k plus 3 all over 2k plus 3 factorial. Here, we're going to get 2k plus 1 factorial. And then here, x to the 2k plus 1. Y'all still all right with that one? Just some algebra, we multiply by the reciprocal. What should you do now? What should we do now? Simplify as much as you can. Now be careful with this. Can you simplify x to the 2k plus 3 and x to the 2k plus 1? I want to say yeah too. So if this is x to the 2k plus 1, this is x to the 2k plus 1 plus 2. Do you see the plus 2 in that? This is x to the 2k plus 1 plus 2. That plus 2 is really just an x squared. Do you get that?
Yes.
Then you get the whole thing, okay? Now, this one's a little weird. We got factorials. We've done this only one time before. If this is 2k plus 1 factorial, this is 2k plus 3 factorial, think about this for a second. 2k plus 3 factorial means, listen carefully, I'm not going to write it again, I've already done it. This means 2k plus 3 times 2k plus 2 times 2k plus 1 times everything below it. So when you simplify this, this end's completely gone. You with me? This one, you have the terms until you subtract down to 2k plus 1. So you have 2k plus 3, no problem. You have the term 2k plus 2, no problem. The next term would be 2k plus 1, would it not?
Yes.
That's going to simplify term by term with this one. So, our limit therefore becomes the limit as k approaches infinity. What do we got?
1 over 2k plus.
Do we need an absolute value here?
No.
You actually don't. You have an x squared, don't you?
Or x.
Positive. These are all going to be positive. Just make sure you put them in the right place. We're going to have a 1 over, what's going to be on our denominator?
2k plus 3, 2k plus 2.
Times x squared. See where x squared's coming from?
Yes.
2k plus 3, 2k plus 1? Now let's do this. Someone have to tell me, how much is this limit always going to be equal to as k approaches infinity?
0.
Always. For any x?
Yes.
Remember, you tell me the x first, right? You say x is blank. I say, okay, pick a k that goes to infinity, and now we take 1 divided by infinity. That's 0. 0 times any number that you've already told me is 0. And this is, oh wait, why is the 0 important? Tell me in relationship with the ratio test why that's important. Lesson 1 says that it converges, right? Now, does it matter the x for which we plug in to get our 0? No, we're going to get 0 no matter what x we plug in. So this thing equals 0 for all x. That means 0 is less than 1 for all x. Can you tell me my radius of convergence?
0.
Radius of convergence is infinity. What's my center? Does it really matter if we're going to infinity?
No.
Not really, but the center is 0. What's my interval of convergence?
Infinity.
So here's what we say, and you write this out. F of x equals sine x can be represented by the series n equals 0, my bad, 0 to infinity of, I'm going to use this series, okay, but I'm going to change it back to n's, just so our format's okay. -1 to the n. It's a dummy variable, it's a dummy k. It doesn't really matter what we use. Dummy. Plus 1 to n plus 1 factorial. On the interval, -infinity to infinity as we just showed. Hang on for 1 second. I know I'm going to go a couple minutes over here, but I want to show you one more thing. It's quite interesting. A quick show of hands if you feel okay with this so far. Now, this is pretty freaking rad, okay? Which means if you want to find out sine of, I don't care what you want to plug in. Sine of 3, sine of pi, sine of pi over 2. I don't care what you want to plug in. All you got to do is plug it in here. Remember, this is the series, right? This is where we got, this is the same thing, this is the same exact thing. So you want to find sine of 3, sine of -2, sine of 1.846, I don't care. Plug it in here, and here, and here, and here, and here, and figure it out for the first however many terms you want to, and you can be as accurate as you want. That's what the power series will do. Now the last thing, very, very fast. This is interesting. Remember me telling you something about how we can take derivatives and integrals of power series? Remember doing that? We did it in the very end of our last section. Well, if f of x equals cosine x, and cosine x is the derivative of sine x, and sine x is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus blah, 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 blah. Check it out. Do you agree that sine x can be represented by this on any interval?
Yeah.
We just proved it. Just showed it. Then if I take a derivative of sine, and I take a derivative of all this crap, what I get, hey, what's the derivative of sine? I'm sorry, what's the derivative of sine? Cosine. So if sine's represented by this stuff, if I take a derivative of sine and I take a derivative of this stuff, the derivative of sine is cosine. Cosine can be represented by the derivative of this stuff, which means 1 minus x to the second over 2 factorial. Look what happened. Bring down the 3. The 3 is going to cross out with this 3 and give me 2 factorial. Plus x to the fourth over 4 factorial. Minus x to the sixth over 6 factorial. Plus. Do you see what happens?
Yeah.
It just lowers everything by 1 power and 1 factorial. Specifically, we get a Maclaurin series of, it's still alternating. It's still alternating. It's still x to a power, but it's only even powers. You don't get the plus 1. Over 2n factorial. Do you guys get that? So we didn't even have to do any work for it. We took a derivative of sine. Derivative of sine's cosine, no problem. Take a derivative term by term. Basically, look at this. This is really cool. Check this out. Could you have done it right from here?
Yeah.
Take a derivative. This goes here, crossed out with 2n minus plus 1. You get 2n. Subtract 1 from my exponent. We get this. Last little bit. What's the interval? Do you remember me telling you that when you take derivatives and integrals, your interval of convergence does not change, only the endpoints. Since we don't have any endpoints, our interval is exactly the same. So, cosine x can be represented by this thing on that interval. Show of hands feel okay with that one? Okay. Okay, so getting to our last example on how to do a Taylor or Maclaurin series from scratch. From scratch means that we invent our own series. After this, what we're going to be doing is using known Taylor Maclaurin series to fit our function to it. You see, that's a lot easier. And so a lot of times we can manipulate what we have into what we've already made. Does that make sense to you? So this is the last thing we're actually going to make. And what it is, it's a polynomial 1 plus x to some power k where k is a real number. So k could be like 1/2. K could be negative. K could be positive, like 2 or 3, in which we would get like a binomial expansion. That's actually what we're going to get anyway. So I'll show that to you right now. So once we start, do you remember the first step when we start any Taylor or Maclaurin series? What do we do?
Your derivative.
Good. So we're going to find a series of derivatives here. We always start with the function itself, f of x, and we find our first derivative. First derivative is going to be, well, if you notice this, it's going to be the chain rule over and over and over and over again. So practically, we bring down the k, we get 1 plus x, the chain rule gives us 1, and then we get k. Very good, that's right. And we keep on going. The second derivative would give us k times k minus 1 times 1 plus x to the k minus 2. Are you hanging on with me here? Okay. The third derivative would give us k, and then would give us k minus 1, and then would give us k minus 2, and then it would be 1 plus x, and then it would be k minus 3. You still okay?
Yeah.
We're just doing a general power rule or a chain rule, whatever you want to call that. We'll do one more. A fourth derivative would be, tell me.
K minus 1, K minus 2, K minus 3, 1 plus x.
Very good. Now, we want to make the jump. How about the nth derivative of f? The nth derivative. Let's look at this for a second. Think about what's going on. What's going on is that I'm multiplying, but it's not quite k factorial. What's happened is I'm doing k, then I'm doing k minus 1, I'm doing k minus 2, I'm doing k minus 3, but I don't get to the k minus n. Do you see it? I get to the k minus n plus 1. The k minus 1 more before that n. Does that make sense to you? Okay. Also, I'm doing my k, well, this is to the k minus n, so let's check it out. First derivative, minus 1. Second derivative, minus 2. Third derivative, minus 3. Fourth derivative, minus 4. Nth derivative, k minus, let's wrap it up. First derivative, k minus 1. Second derivative, k minus 2. Third derivative, k minus 3. Fourth derivative, k minus 4. Nth derivative, k minus n. Perfect. That's exactly right. Now, all this stuff, I gotta rewrite this, I need more room. So, nth derivative, 1 plus x to the, you just said it, k minus n. Are you guys alright with that one?
Yeah.
Now, here, we'd have k minus 1, we'd have all the way down to k minus, what's this number in relation to my n?
1 minus 1. Like 1
N
less.
minus 1.
It is n minus 1, that's right, but check this out. We'd have k minus n minus 1. Do you guys see what I'm talking about here?
Yeah.
This would be k minus, oh, n minus 1. K minus, oh, 3 minus 1. Oh, k minus 2 minus 1. K, well, where'd it go? K minus 1 minus 1, just k. So if I had k minus n minus 1, the n minus 1's got to be in parentheses. Do you understand what I'm talking about?
Yeah.
Well, if I am to distribute this and make it a little nicer, this is k minus n plus 1. K minus n plus 1. Let's see if it works. We got our k. Sure, we got our k. Let's see how this works. Is this k minus 2 plus 1?
Yeah.
Yes.
Minus 2 would be, well, negative 2, then plus 1 gives us minus 1. Here would be 3. 3 minus 2 plus 1. Got it. And then we'd have minus 4 plus 1. That's 3. I think I said that one backwards. I said minus 3 and then plus 1, that's minus 2. Minus 4 plus 1, that's 3. Minus n plus 1. And that's where we would stop. Should hands feel okay with that so far? Now, we actually have a pattern for our nth derivative of f, which means that if I want to find what I want to do here is find the Maclaurin series. So if I want to find the Maclaurin series, what I want is the nth derivative of f at 0. The Maclaurin series says it's centered at 0. You with me on this one? Well, let's do that. What number am I going to plug in, and where am I going to plug it in?
0 for x.
So that's what it says right here. So if I plug in 0 for x, what's 1 plus 0?
1.
1 to any power.
1.
So this whole thing is going to become 1. Essentially, I'm just going to get this piece back again. Do you see it?
Yeah.
So k, and then k minus 1, and then all the way down to k minus n plus 1. Okay, show of hands, feel okay with that so far? Guys over here, yes, no?
Yep.
All right, so if we're looking for the Maclaurin series, here's what we're saying. We're saying the Maclaurin series should represent a function f of x, in this case 1 plus x to the k, by doing this. It should be a series which starts at 0 and ends at infinity. It should be the nth derivative at 0. It should be over n factorial times x to the nth, if that's a Maclaurin series. Does that look familiar to you?
Yeah.
That's our Maclaurin series. All right, cool. Well, hey, you know what? This part is going to be there no matter what. It's centered at 0, yeah? That's why we have Maclaurin series. This is over n factorial. Not a problem. This one, do we know our expression for the nth derivative of f at 0? In fact, we just found it. It's right there. So now we say, okay, this series is n equals 0 to infinity. We've got, oh my gosh, k minus 1, k minus 2, all the way down to k minus n plus 1, all over n factorial times x to the n. Goodness gracious me, that's a lot of stuff. Okay, what I want to know is by show of hands, you feel okay getting that far? Do you? Do you see where it's coming from? Do you see where all our derivatives are coming from? Yes, no? Why we stop at k minus n plus 1. Do you see where that's coming from? All right, well, if we plug in 0 for x, which is our center, it's a Maclaurin series, it says c equals 0, no problem, just plug that in. So at 0, we get, this thing's gone. We get just this piece. By definition, a Maclaurin series is the nth derivative of f at 0. Hey, that's right here. Times x to the n, okay, that's right here, all over n factorial. So we have the nth derivative of f at 0. We got x to the nth, we got n factorial. Hopefully it's clear for you, it's just a Maclaurin series. You guys with me on it?
Yeah.
Now, let's do the first few terms of this to see what it really looks like, because many of you are probably going, how in the world am I going to do that series? What in the world does that look like? Here's what it looks like. This series looks like this. So really, you could represent 1 plus x to the k by doing these terms. The first term is going to be 1. The first term is going to be 1 because remember what the Maclaurin series represents. Are you listening? The Maclaurin series represents f of 0 first. F of 0 says I just plug in 0. I would get 1. 1 plus 0 is 1 to any power gives you 1. That would be my first term. Then I would get the first derivative at 0. The first derivative at 0 would give me k, but then I'd have my x from my power series. I'd get kx all over 1 factorial because I'd be at my first term. Are you guys all right with that so far? So this, practically speaking, just represents these guys right here. Then we multiply by x to whatever our n is and divide by n factorial. So here we go, okay. At 0 term, I'd get f of 0, that's 1, times x to the 0th power, that's 1, divided by 0 factorial, that's 1, so we get 1. The next term says, okay, cool. Well, we get k times x to the first over 1 factorial, that's kx. Then we would get k times k minus 1 times x to the second all over 2 factorial. Are you starting to see the pattern at work now? Yes, no? You sure? Okay. Then we keep going. We get k. We get k minus 1. What's the next term? Actually, factors would it be. And then what? X to the third all over. Perfect. That's what this thing looks like. You go, okay, cool. It starts at 1 because the Maclaurin series says you start at the function evaluated at your center. Are you listening? You start at your function evaluated at your center. In a Maclaurin series, that center is 0. So you start at f of 0. That would be 1 to, I don't care what it is, 1 to any power is 1. You start at 1. And multiplied by x to the 0th over 0 factorial. That would be 1 over 1, that's giving you 1. Then you do the first derivative, evaluated at your center. The first derivative, evaluate your center is 1 times k. So it's k times x to the first all over 1 factorial. That just gives you k times x. Does that make sense? Then you do your second derivative, evaluated at your center, x equals 0. Okay, well that's 1 times k. Okay, so we get k times k minus 1, hey, times x to the second over 2 factorial. That's where these things are coming from. That's where they're coming from. The next one would be k times k minus 1 times k minus 2 times k minus 3, x to the 4th over 4 factorial, and you'd continue forever. Does that make sense to you? What this is called is the binomial series. Binomial, 2 terms being expanded. So this is the binomial series. And we can make this series look a little bit different. What this actually gives you here, these things, give you the binomial coefficients. Do you know what the binomial coefficients are? Have you ever heard of Pascal's triangle? If you took me for Calculus 1, you have heard of that. Pascal's triangle goes 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Have you ever seen that before?
Yes.
That's what these numbers are. 1. And then, well, whatever k you have, it would depend on that. But that's what the binomial coefficients are. So this thing, this gives you, this 1k, this gives you the binomial coefficients for whatever k you actually have. Isn't that kind of interesting? It's going to give you a line of Pascal's triangle. What does Pascal's triangle always start with? 1. And then it depends. It's going to either do, well, 1, 2, and then 1, 3, 1. Oh, look at that. Whatever your power would be. That's weird. That's kind of cool. So if you have a power of the 5th, I'd be down here. 1, 5. It'd be 1, 5, 10, 10, 5, 1. That's interesting. So this would be 1, 5. This would give me 10. This would give me 10, 5, and then 1. That would be my binomial coefficients. So the way that we write that, actually, since these only represent your binomial coefficients, we can write it this way. This series is represented by k, n. This stands for binomial coefficients. Like that. So what I want you guys to know about this thing is that this idea, this whole thing from here to here, all they give you are the terms of Pascal's triangle. Those are the binomial coefficients. This is represented by that, just to make it look nicer. So if you've ever seen that before, that's what that is. Quick head nod if you're okay with this so far. Would you like an example to see how this actually works in practicality? Okay, before we do this, I want to give you a couple notes. Here's your notes. If k, do you have this written down? Because I'm going to erase this for some room. So these are binomial coefficients. These are binomial coefficients. These are binomial coefficients. That's it. If k is a positive integer, give me an example of a positive integer, please.
4.
Good. What else?
2,
1. And?
Any positive number.
100.
Not any positive number. No. 1.3 is not a positive integer.
Well, integers of
Positive whole number. Very good. A positive whole number is whole numbers are inherently positive. So a positive integer are whole numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, not 0. Does that make sense to you? So if k is one of those, if k is a positive integer, then this series will converge for all values of x. Okay, so let me put this in other words for you, okay? Let's say that your function was 1 plus x to the third. Is that a positive? Is 3 a positive integer?
Yeah.
Then this series is going to represent this function for any x that you put in. Any x. Does that make sense to you? If this was if the k was now -4, is this series going to represent that for any x?
No.
No, but it will represent it for a different set of numbers, okay? So here's the other choice, I guess. If k is not a positive integer, this series will converge, but it's only going to converge if x is between -1 and 1. Oops. More specifically, if k is between -1 and 0, we get to include the endpoint +1. If k is greater than or equal to 0, we get to include both endpoints. If not, we don't include any endpoints. And that would be by the ratio test. So let me go through it one time as far as all this conversion stuff goes. You ready? I'll give you an example in just a minute. We'll go through it pretty quickly, but we'll give you an example here. So, binomial series, no problem, those are binomial coefficients. What this series will do, this series will converge and represent this function if k is a positive integer anywhere. Anywhere. 1, 2, 3, 4, 5, 6, 7, 8. If k is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, forever, no problem, then this series will converge for any value of x that you want to put in there. Do you grasp that? Your interval of convergence is -infinity to infinity, not a problem. It will always converge. Now, if k is not a positive integer, that would be 1/2, -4, -3/2, whatever it happens to be. This series will converge. It will represent your function, but only on the interval of -1 to 1. X equals -1 to 1. Those values of x will make the series converge if k is not a positive integer. Have I explained that well enough for you? Now, there's more specifics to it. If k happens to be between -1 and 0, you get to include the endpoint of this interval, 1. If k happens to be between, well, not between, sorry, positive, so greater than or equal to 0, then you include both of those endpoints. That's the idea here. Show of hands if you feel okay with that one. Now, let's do an example here real quick. Does this fit our binomial series that we want?
I think so.
Does this look like this? something to the k power?
Yeah.
Yeah.
How?
X plus one quantity to the 1/2.
What's our k?
1/2.
1/2.
Okay, good. Now, can we represent this with a Taylor series or a Maclaurin series?
Yeah.
Yes, we can. And tell me something. Will the series that we get converge? They all converge. Where will it converge? For all x or between -1 and 1?
-1 and 0.
Okay, now let's think carefully. So we're not here, right?
No.
K is not a positive integer. K is positive. Is k between -1 and 0?
Yeah.
Is k between -1 and 0?
No.
Is k bigger than 0?
Yes.
We're here. Okay, if we weren't here and k was like negative, let's say k was -1/2, we'd be here. Let's say that k was -2, we'd be here. Does that make sense to you? Okay, so here's the deal. We can represent 1 plus x to the 1/2 power by listing out these terms, these binomial terms. So what we do is we'd say, all right, let's just follow this for right now. So we're going to start with what? Good. 1. We always start with 1. That was the easy one. Okay, let's continue. What's the next term? What's our k?
1/2.
So we would have 1/2 x plus. What's our k again?
1/2.
So we have 1/2 times 1/2 minus 1 times x squared all over. So 1/2 times 1/2 minus 1 times x squared all over 2 factorial. Then we have what?
1/2.
1/2. Very good. Keep going.
Times 1/2 minus 1. Times 1/2 minus 2.
Times.
X squared.
Could you do the next terms if I asked you to?
Yes.
Okay, very good. Now, ultimately, what we're going to get down to is we're going to get this. We're going to get down to 1/2, 1/2 minus 1, 1/2 minus 2, 1/2 minus n plus 1. Do you remember that term? K minus n plus 1, okay. And we would have x to the nth all over n factorial. That's where we would end. Now we're going to simplify this a lot. So we got to look at what these things are actually doing, these fractions. What we're going to do is we're going to take these fractions, simplify them, and look how that affects our problem. Are you with me? You sure you're with me? Okay. Let's think about 1/2 times whatever this happens to be. What's this going to give you? Okay, remember what we do with patterns? What we do with patterns is we don't really multiply things. I know it's -1/4. But what I want you to see is that this is really -1 over 2 times 2. Do you see it? 2 squared. This one would be 1/2 times 1/2 negative times -3/2. Am I right?
Yeah.
Or would it be positive or negative?
Positive.
Positive, and you would get 3 over 2 cubed. Are you with me?
Yes.
Okay. Let's put this together then. So what this becomes, we'd start with 1. We'd have 1/2 x, but then the next one, check this out. This is where the pattern actually starts. So positive, what's the next term going to become? We're going to have x squared all over 2 factorial times 2 squared. This right here is -1 over 2 squared. If I take this, this goes on my denominator. This negative changes that to a minus. I have an x squared on my numerator, I have a 2 factorial on my denominator, and now I have a 2 squared on my denominator. The algebra can be a little tricky if you're not super good at algebra. Do you see what I'm talking about here?
Yeah.
Are you sure? Have I lost you? I don't want to lose you. Okay, let's go to the next term. Come on, stick with me here, folks. Do I have a plus or a minus?
Plus.
It's going to be a plus because it's positive. I'm going to have an x to the third on my numerator. Do you see why? Now this was 3 over 2 cubed. So what I get is, where would the 3 be?
Down.
The 3 would be on the numerator. Where would the 2 cubed be?
On.
3 factorial times 2 to the third. Does that make sense to you?
Yeah.
Okay, now the next one. Let's see about the next one. Do you suppose the next one's going to be positive or negative?
Negative.
Okay. On the numerator, do you understand I'm going to have an x to the fourth?
Yeah.
Yes.
Do you understand that I'm going to have a 4 factorial somewhere?
Yeah. Yes.
Okay. Do you understand I'm going to get a 2 to the fourth?
Yeah.
Now these numbers are interesting. This goes 1, see where the 1's coming from?
5.
3. It's actually, it's 1 times 3, isn't it? This is 1 times 3 times 5. The next one would be plus 1 times 3 times 5 times 7. X to the fifth over 5 factorial to the fifth. And that's the pattern we're looking for. The last term, as we end this, it's going to be, there's actually no really good way to write this pattern. It's 1 times 3 times 5. You got to write that out and then go, okay, well, where's it ending? It's ending at 2n minus 1. It's ending at an odd number, 2n minus 1. I'm sorry, 2n minus 3, because the minus 1 would give us 2 much bigger, or 1 bigger, minus 3. X to the n, all over, let's see if it matches. This is our n, matches our factorial, n factorial, 2 to the n. Now, because this pattern starts at the second term, we're going to define it this way. So what we know, we can represent this function 1 plus x to the 1/2 by doing this. Do you guys see what I mean about the pattern starts at the second term? This pattern doesn't really start right here. This is positive, positive, and then we go negative. The pattern starts here. So you can define a series like this, or a function like this. Define it like, okay, well, we got 1 plus 1/2 x plus, and then we're going to start with our series. The series does this. It starts at if this is the 0th term, and this is the first term, our n would be starting at the 2 to infinity. We got to start with, look at this. Do you guys see that I have the same 1? I get the same 1/2, and then I have a minus. I got to start with a negative term. So what we're going to do is say, I want this -1 to start by being negative. How can I do it? I can do n minus 1. We're going to use n plus 1 just so we don't have any problems with it. We can do n minus 1. I think n minus 1 will work as well. So n plus 1, did you see that's going to be the same exact thing?
Yeah.
Negative, positive. Okay, cool. After that, well, we have, man, the pattern starts. The pattern does this. Omit these first 2 terms. That's what this does. It says, hey, put the first 2 terms. Then start your series. This is like where we start our series. Start your series with a negative, then make it a positive, then a negative, then a positive. That's what this is doing. Start with a negative, then doing positive, then negative, then positive. Are you with me still so far?
Yeah.
The numerator of your series does this. The numerator goes 1, 1, 3, 1, 3, 5, 1, 3, 5, 7, 1, 3, 5, 7, 9, blah, 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 multiplying by all the previous odd numbers. It's not a factorial, because you're not multiplying every single number. You're multiplying only the odd numbers. The only way we represent that is by showing it. Then we do 1 times 3 times 5, and then you say, you're going to stop at, well, what we want to stop at is, let's see, this would be, compared to this n, this would be 2 times 5 minus what to get this? 2 times 5, because we want to base it on n, right? And it's got to be odd, so it's 2 times something minus 1 or minus 3 or minus 5. Well, to get this number, it's 2 times 5, which is 10. 3, not 1. It's not stopping at 9. It's stopping at 7. One odd number before that. So we're going to stop at 2n minus 3. That's our numerator. Our denominator is only n factorial, no problem. 2 to the n, got it. And then we have x to the n. And that's about the nastiest freaking thing that you've probably ever seen, yeah?
Yeah.
Crazy?
A little bit.
Do we have to check for convergence?
Yes.
No.
No.
No, because we already did it. I already proved it to you in the very first example we did today. So what we'd say is that, so, f of x can be represented, that's what this means, f of x can be represented by this series on the interval. What's our interval?
Negative 1 to 1, including both.
Why including both?
It's greater
That
than
x
0.
is,
Good, yeah, x is, the k is greater than 0. It's not between negative 1 and 0. Also, this would be all real numbers if k had been what?
Positive.
Positive integer, that's exactly right. So we'd say this. We'd say that our function can be represented by this really nasty series. We know it's going to be convergent because we already proved why. We already showed that. If k is positive integer for all real numbers x. If k is between negative 1 and 0, then it's for x equals negative 1 to 1, but only including the endpoint 1. If it's outside of that range, if it's less than 1, less than negative 1, then it's only for negative 1 to 1, not including any endpoints. For us, we say, hey, look at that. Our k is not a positive integer, but it is positive. If our k is not a positive integer, but it is positive, we include both of our endpoints. It goes from negative 1 to 1. That was a crazy example. Show of hands if you hung with me or okay on it. It's a little weird, right? Is it going to take some maybe thinking about later? Maybe. Maybe watch this part again. Now, what we're going to do from here on out, I'm going to show you how to make your given function fit a series we've already done. I'm going to list out some series. Most of them we've done already. The last two, well, there's 2 or 3 of them that we haven't. Are there any questions?
No.
Thank goodness. Okay. That's great. Okay, I need you to write this quickly. We've already done them. They are in your notes. I'm just recapping here. So here's some common Maclaurin series. Ooh, that's smaller, I think. All but these 3 we've worked with. So what I'm going to do for you is I'm going to give you what these series look like. I'm going to give you the actual series notation for it. And I'll show you how to work with them because it's going to be really nice, I promise. You're going to like this better than what we just did. Well, that's not saying much. Anyway. So here we go. What this series is, do you remember doing that? It's one of the first ones we did.
Yes.
We took an integral of this, it became negative ln of 1 minus x, and then we divided, and we got this. We got, well, that represents ln. But this series is represented by 1 plus x squared, because what it really is simply a geometric series. Remember that? A was 1, r was x, bam. This is our geometric series. And it was simply represented by this. And the interval of convergence was negative 1 to 1. E to the x was a nice one. It was 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus, and that's the series from n equals 0 to infinity of x to the n over n factorial, and that converged for all real numbers. Sine. We actually did. Do you guys remember doing sine? Remember doing some of these ones? We worked through them. This is all of our examples. We made them from scratch. Sine was this. It was x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus, and that created the series for us from n equals 0 to infinity, -1. It was alternating, obviously. X to the odd, 2n plus 1, over 2n plus 1 factorial. And it converged for all real numbers, x. Does that one look familiar to you?
Yeah.
We did it yesterday.
We did? Oh, perfect. So it looks familiar. Cosine. Cosine was really easy.
Same
Cosine
thing.
was just the derivative of sine. 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus blah, 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 blah. We said, hey, it's still alternating. It's now x to the even numbers over even numbers factorial. And it converged from -infinity to infinity. Oh, that's the last thing we did. That's right. Okay, ln of 1 plus x. ln of 1 plus x. We have x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4. I don't remember if we did this one or not. This is the series from n equals 0 to infinity, -1 to the n minus 1, x over n all over n. And you can see that right here. It's kind of a nice one. This converged on -1 to 1. Positive 1 was included, -1 is not included. You know, I'll probably move the last two over there, just to be clearer. Sine inverse of x. We would have x. We would have, no, we have not done this one, okay? I'm just giving this to you so you have it. We actually do x cubed over 2 times 3. We would do 1 times 3 x to the fifth over 2 times 4 times 5. And what this ends up being in the series, which is quite interesting, we start at 0, we go to infinity. We have 2 to the n factorial, x to the 2n plus 1, all over 2 to the n factorial squared, times odd numbers. These ones I gotta. Tan inverse of x is this. X minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7, or, in other words, it's an easy one. Looks nice at least. We get alternating. We get x to the odds over odds. Do you see how similar tangent inverse is to sine inverse? It's really similar, except that's a factorial. Really similar though, it's interesting. And tan inverse only converges on -1 to 1. Inclusive. So does sine inverse. Okay, last one, we just did it. If you have 1 plus x to the k, this thing is equal to the series, we just showed it, n equals 0 to infinity, I'm not going to go through it again. Binomial coefficients times x to the n, and it converges on -1 to 1. Converges on -1 to 1. If k is, and there's special cases, okay? If k is positive integer, it's all real numbers. If k is between 0 and -1, then we get 1 included. If we get above 0, then we get both endpoints included. So there's special cases there. Now, here's the point. Let me make sure I got all these right, too. I definitely don't want to give you the wrong stuff here. I was writing them pretty quickly.
I think you forgot cosine inverse.
No, I didn't forget it.
Just now.
Cosine inverse. No. I think cosine negative 1.
That looks good. Perfect. Got it. That one's so nasty. That's good. Perfect. All right, now, here's the whole point. The point that I'm going to make here is that you can manipulate functions that you're given to fit these forms. And if you can do that, then you don't have to reinvent the wheel, basically. You don't have to start from scratch on these problems. Have you written this down? Because I'm going to erase it here real quick, because I need to start here. Do you have it?
Yeah.
This one you already have, so just worry about that one. Can I erase it? Yes, no?
Yes.
Yes.
Okay, good.
Get that message.
For example, let's say I give you this function on your test, which I'm going to do. And I say, I want you to find the Taylor series at this point. So I want Taylor at x equals 2 or c equals 2. We'll go for it. Now here's how to diagnose the problem. If you're going to have a Taylor polynomial, or not Taylor polynomial, I'm sorry, I'm skipping ahead. If you're going to have a Taylor series at the point x equals 2 or c equals 2, what that means is that somewhere in your series you are going to have x minus 2. Does that make sense to you? No. I can tell by the
Yes.
blank looks on your faces that you're like, what? What are we talking about? If you're going to have x equals 2 or c equals 2, whatever I want to say there, then you're going to have x minus 2 somewhere in your Taylor series. Do you remember your Taylor series says x minus c?
Yes.
You're going to have x minus 2 here if your c is equal to 2. Show of hands if you feel okay with that one. Okay, here's what you need to do. Whatever your center is, if you have x minus 2 or x plus whatever, c equals 2 or c equals whatever, get x minus that number in your given function. You must make this up here somewhere. So what that means is that I've got to manipulate this such that I find this in here. Are you listening? I'll show you. If you don't, what in the world are you talking about? I'll show you, okay? You got to manipulate this to get my x minus 2. So here we go. From 1 over 1 plus x. Well, I think about it, 1 over 1 plus, I would do x minus 2, but then I have to undo it. Plus 2. Can you follow that one? I'll do it one more time. I have this, I need this. So if I'm centered at 2, I'm going to have an x minus 2 somewhere in my problem. I have to have that. So my 1 over x plus whatever, I'm going to say, all right, cool. Well, 1 plus x, no, I need an x minus 2. That's what I need. Does that make sense to you?
Yes.
I can't just arbitrarily subtract 2 from my problem, though. If I subtract 2, I'm going to have to add it back. It still has to equal this thing. Does this still equal that?
Yes.
Sure it does. Now let's simplify. 1 over 3 plus x minus 2. quick show of hands if you feel okay with that so far. Do you see that we have the same function? It's just we've made this piece in it. It's going to be a Taylor series. It has to have x minus 2 up there somewhere. That's our center. You've got to find your center. Okay? You got to be centered here. Now, take this and actually look at this one. What does this most closely match out of all of these? Does it match sine inverse?
No.
No, it doesn't. Does it match e to the x?
No.
Does it match 1 over 1 minus x?
Yes.
That's the closest. That's what we're going to try to fit it. So we need to make this thing fit this thing. Now, when I say fit this thing, we need to make it fit 1 over 1 minus, I'm going to put x here in quotations. X stands for some quantity. It can be a really nasty looking thing, but it stands for x, like whatever's there. And then whatever's there, we're going to take it and put it here, and here, and here, and here, and here, and we're going to get that thing out of it. Let me show you. So if I need to make this fit 1 over 1 minus x, I need to manipulate this so that this thing becomes a 1. Can I do that? How do I do that? If I factor out a 1/3, I would get 1/3 times 1 over 1 plus x over 2, x minus 2 over 3. Can you do the algebra on that to make sure that that's okay with you?
Yeah.
Distribute the 3. Here's 3, here's x minus 2. Do you guys follow?
Yeah.
Now, this is very close. This is 1 over 1 plus something, some bunch of crap, okay? I want 1 over 1 minus. I gotta change it to a minus. It's gotta fit this. So I'll have my 1/3. I'll have my 1 over 1 minus. But then this, how can I make that minus? How can I make a plus equal a minus something? You can't do negative x plus 2. Explain me why you can't do negative x plus 2. Boom. You have to have that. Does that make sense? So you've got to have that as your center. That's got to be there. It's okay. It's basic algebra. It really is basic algebra, but you feel okay with it. Is this thing still this thing? Yeah, just nasty looking. Now here's the cool part. This is where the rubber hits the road, all right? This is what's awesome. What this really is it's 1/3. But inside here, do you see it's 1 over 1 minus x? It's just our x, our junk, is this junk. That's our junk. Are you sure you're okay with it? Do I need a 10-second recap to go over it, or are you sure you're okay?
Yes.
Some of you don't look okay. Make this here, because that's our center. X, if it's 2, you gotta have x minus 2. Put that up there. Yeah, you gotta add 2 to it. Simplify it. Make it fit one of these things. In order to do that, we need 1 over 1 minus junk. X is your junk. Okay, if I need 1 over 1 minus junk, right now I don't have it. Make this a 1. Divide by 3. Got it. Make that a minus. Split off a negative. Now I got it. Now it's 1 over 1 minus junk. Cool?
Cool.
Take this thing, fit it to this stuff, and then see what happens. So if we see what happens here, we're going to fit it to this formula. What's our formula start with?
1.
Yep. The next thing we have in our formula is what?
X.
Notice how x is the junk. This is the junk. You sure? You okay with that?
Yes.
So 1 plus, we have negative x minus 2 over 3. So far, so good. Are you sure you're okay? I don't want to leave you behind here, because this is very important for us to know. We have 1, we got 1. We got junk. Here's junk. Put your junk. Next thing we do.
Junk square.
Yeah, junk squared. What's in between there?
Plus.
Okay, plus, I don't like to say the whole thing, so yeah, junk squared. Minus 2 over 3, whole thing, plus. Let's do the next one and then we'll stop. What's the next one? Plus junk cubed. plus blah, 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 blah. We're going to go forever and ever and ever. Okay, I need a show of hands if you think that you can make it from here to there. Show of hands if you can do that. It's not that bad, right? You just put the, whatever your x is. This is the important part. This is the hard part, making it fit. After you make it fit, just put this in here. It's 1 over 1 minus x. It's 1 over 1 minus x. Put it here and here and here and here and blah, 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 and then see what happens with your series. Now, there's one thing that we're forgetting. What are we forgetting? The 1/3 is multiplied by all this stuff. Don't worry about that right now.
I've forgotten about that.
Don't worry about that right now.
Wrong on the test.
Yeah, don't do that. We're going to use one of these later, so. Okay. Let's keep on going. Let's take this, let's simplify it. So if I take that, and remember, oh man, remember, we are looking for patterns here. We're looking for patterns. So what I'm not going to do, I'm not going to go 9 and 27. What I'm going to do is I'm going to keep the 1/3. I'm going to do a 1, I'm going to do a minus. So notice how that's a minus. We got x minus 2 over 3. What's the next thing we're going to have, a plus or a minus? We're going to have x minus 2 squared over 3 squared. Yes, no?
Yeah.
We're going to have a minus. X minus 2 to the 3rd over 3 to the 3rd. Then it's going to be a plus. And then so forth and so on. Can you make it down that far with me?
Yeah.
You see where we're getting the x minus 2 to the 1st and to the 2nd and to the 3rd, yeah?
Yeah.
We get to the 1st and to the 2nd and to the 3rd. We're doing positive, negative and then positive and then negative and then positive. And we have 3 to the 1st and 2nd and 3rd and 4th. Now we're looking for a pattern here. So check it out. Let's fit this to our pattern. This is 3 to the what power? Nope, this is 3 to the 1st. This is 3 to the, aha. That's going to give us our 1. So we start with 1, x minus 2 to the 1st, x minus 2 to the 2nd, and then 3rd. We got 3 to the 0, 1, 2, 3. Can we go ahead and make a series out of this in series notation? Sure. Here's how you do it. The 1/3 starts out front, and you multiply, make this your series. Our series starts at n equals, good, 0. It goes to infinity. Tell me something about this series that we know. It's alternating, and it starts with a positive. So we're going to have -1 to the n, because that's going to start positive. The next one would be negative. The next one would be positive. Does that make sense to you?
Yeah.
We're going to have x minus 2 to the,
And
very good, all over 3 to the n. Perfect. That's exactly, you guys are getting it. Yeah, this is 3 to the n. Hey, 0, 1, 2, 3. Here's x minus 2 to the n, 1, 2, 3. Here's starting positive and going alternating, no problem. There's one more thing we got to do. It's very easy. Take the 1/3 and move it inside. So if you have 1/3 times this, do you understand this is 3 to the 1st?
yeah.
Yep. If you have 3 to the 1st times 3 to the n, you get 3 to the n plus 1. Now wrap it all up. F of x equals 1 over 1 plus x can be represented by this on the interval. Oh, wait a minute. We forgot all about the interval, didn't we? Do we have to check the interval?
No.
No, it's already been done for you, which is why we use these things. No ratio test, no endpoint test, no nothing. Look at the board. Which series did we use? What's the interval of convergence?
1 to 1.
Same thing here. Pretty cool, right? You can make them fit. This is one of the harder ones that you're going to do. Now, we're almost done with it. Almost. I kind of lied a little bit. This would work. This would work if your x was just x. But keep in mind, don't stick with me here for just a second, okay? This would work if your x was just x. But your x that you used here is your junk. Okay, so we have one more thing to do. Remember that your x works between -1 and 1. Do you follow?
Yeah.
Okay. Just put your junk into where this junk
Is.
is.
Okay.
So, what's your junk?
X minus 2 over 3, negative.
Negative. Okay, so negative x minus 2 over 3. That's your junk. Multiply by 3. Oh, wait a minute. What's negative do to inequalities?
Just flip some.
Add your 2. Flip it back around. We get the interval -1 to 5. Take your function, make your center fit. After you make your center fit, manipulate it so it fits one of your series you already know. After that, use it. Your x, whatever your x is up here, is whatever your junk is here, whatever you made it fit as, okay? So this right here, this becomes your x. Just don't forget that at the very end, when you get all this stuff done, when you find your pattern, when you make your pattern work, it's not going to be that hard. When you make your pattern work, take your junk, put it back into your interval, and then solve for it. Solve for what that interval is. Does that make sense to you?
Yeah.
Okay, now I'm going to pause the tape here real quick. If you need to go, you may go. I'm going to stay here for another 30 minutes or so and lecture. I'm going to put this on videotape, so if you want to just do this later, you can. But so if you need to go, go. I don't want to make you any later than you are for whatever you want. So I'm going to give you about 30 seconds. If you want to head out, head out. You're not going to offend me, okay? If you want to stay, I'm going to be lecturing. I think you're going to enjoy it if you do stay, but if not, have a great spring break. Okay? 30 seconds. Go or stay.
Doesn't look like something I can afford to miss.
You can watch it. It's going to be the same.
It's not the same. It's not the same. It's
Oh, I don't want to do this to you guys if you really need to go.
no. Oh no, it's fine.
Okay. All right. So now we're going to continue. So I understand. Did this make sense to you? Did you grasp that? You go, okay, take your junk, plug it in, no problem. Just don't forget about your interval. Your interval, yeah, it's going to be based on this, but this says that your x, your stuff, is going to be between -1 and 1. Solve for your actual x, and you get here between -1 and 5. Now we're going to continue. We have about two and a half more examples. They're going to go quicker now that we have this idea. So what I'm going to do is I'm going to put up the example. We're going to talk about what series we're going to base it on. I'm going to show you the things that we can do. And so next example. What I want to do with this, I want to find the Maclaurin series. You'll notice that in the previous example, we based it on a Maclaurin series, didn't we? Because I gave you common Maclaurin series. If you need a Taylor series, you have to fit the x minus the center in there. Not a problem. If you want a Maclaurin series, it's even easier. So if I have x squared sine of 2x, well, what series are we going to base that on? Sine x. So what we know is that if sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus blah, 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 blah. If that's the case, look at what we can do. It's so nice. All we got to do, all we got to do, well, is this exactly like this? Is this exactly like this?
No.
Exactly like this? No. This says sine x, this says sine 2x. Don't fret, don't worry. if sine x equals this, then sine 2x equals, plug it in, 2x minus 2x to the third over 3 factorial plus 2x to the fifth over 5 factorial minus, and you keep going like that. Notice how here, I keep using the word junk, I'm going to still. Your x, your junk, is now 2x. So you just plug it in. Now, fortunately for us, because we have the Maclaurin series, you don't have to fit an x minus anything. It'd be 0. It would just be x. Does that make sense to you? So cool, all right. Well, your junk is 2x. Just put it in here. We got 2x. We got 2x cubed. We have 2x to the fifth. Show hands feel all right with that one. All right. Now, oh man, is this the same as that?
No.
No, but it's really close. So if that's not the same, what else could we do? Say what now? How do I make this look like this?
Multiply by x squared.
You could actually do that right now if you want. I'm going to show you how to do it later. It's really easy. So I prefer doing it this way, but you could multiply by x squared everywhere. You could do that. It's going to come out exactly the same. It's just the pattern's a little harder to find. So we're going to start finding this pattern right now. So working on the pattern, let's see what it actually does. What this is this would be 2x. No problem. This would be, remember I'm looking for patterns here. So I'm going to have 2 to the fifth. No, I'm not. I'm going to have 2 to the third, x to the third over 3 factorial. I'm going to have 2 to the fifth, x to the fifth over 5 factorial. I'm splitting these up for a reason. The reason why I'm splitting them up is because I'm going to be multiplying by x squared later, and so I'm going to have to split them up at some point or another. I'm going to split them up right now. Show of hands if that makes sense to you. Now let's make our series. We're about good to go on this. So our series starts at 0. It goes to infinity. Tell me something about this series that you know. Yeah, it's alternating. And it starts off with a positive. So that would be n. That's right. Tell me something else about this series.
Odd numbers.
It's odd numbers. That's right. It's taking two odd numbers. It's taking x, 2 odd numbers. All over odd numbers factorial. We have to use a +1 here for our odd numbers because we're starting at 0. Do you guys see what I'm talking about? If we start at 0 and we get a 1 and a 1, this is, well, at your 0th term, you're actually getting 1. So 2 times 0 plus 1 gives us 1. 2 times 0 plus 1 gives us 1, all over 1 factorial. So we're starting, it says 0, but we have to make them odds, but we got to start at 1. So it's not -1 this time, it's +1 GCY. Did I lose you?
You're going.
Does that make sense? Okay. So here's what we know. We know that this thing, sine of 2x, would equal that series with no problems. Now, how do I get from sine of 2x to what I want? You can do things like that. So if I multiply by x squared, and I multiply by x squared, listen, it's an equation, okay? It's going to work. This thing is represented by this series. Therefore, x squared times this thing is represented by this series times x squared. Therefore, x squared times sine of 2x is equal to our series. We go from 0 to infinity, -1 to the nth, 2 to the 2n plus 1. What's that going to be?
2n plus 3.
2n. Yeah, do you guys remember that? You're adding exponents. So 2n plus 1 plus 2, that's 2n plus 3. Now I'm going to stop for just a brief moment. Do you understand that you could have multiplied by x squared here and got the same thing? It's just your 2's would be different than your x's. So your powers of 2 would be different than your x's. Is this going to change to 2n plus 3? Now we're almost done with this one too. They're going to go quicker after this. Look back at your notes and tell me the interval of convergence for our sine. not sine inverse for our sine.
Negative infinity.
Negative infinity to infinity. What that means is that if our sine is convergent on negative infinity to infinity, our sine of 2x is also convergent on negative infinity to infinity, and even when I multiply by x squared, it's still convergent on negative infinity to infinity. So what we say, we wrap this thing up, and we would say that f of x equals x squared sine of 2x can be represented by our nasty series on negative infinity to infinity. And if you forgot what that means, here's what it means. It means this. If I want to find out this as evaluated at any number, I could actually do it with this series. I could plug in my, give me a number, any number.
3.
3, plug in 3. If I wanted to plug in 3, I could actually represent it by plugging in 3 to this series, working it all out to infinity, and adding it all up together. And it will work for any value. What it says is that this series will converge for any value of x. Therefore, for any value of x, this series, this power series, Taylor series, Maclaurin series, will represent our given function. Show of hands if that one made sense to you. So, can you manipulate what you have to get what you need? Sure. Multiply this by 2, you get this. Find your pattern, find your series, multiply by x squared, no problem. Just a couple more. The reason why you don't have a whole bunch of other Maclaurin series, why you only have a set amount of them from me, is because a lot of times you can manipulate what you're given to what you want to get. Remember cinch? Remember the definition for cinch? No, we don't. It's a. Do you remember what it means?
Hyperbolic?
That's what the H is. Very. At least we understand that. Okay, so, well, if you don't remember it, here's what this meant. This meant e to the x minus e to the negative x all over 2. Do you remember that one?
Yes.
Okay, cool. Well, if you split this up, then what we really have here is a combination of 2 different series, which is really cool. So think about this. Look back at your notes and you tell me what e to the x equals as far as your series is.
X to the n over n factorial.
You know what, that's great, but we're going to have to do it term by term because we're going to have to find this pattern because we're going to be combining 2 series, okay? So tell me term by term what e to the x is represented as. 1 plus, say it again?
Plus x.
Keep going.
Plus x squared over 2 factorial. Plus x cubed over 3 factorial.
And Patrick's right, that would be x to the n over n factorial. Quick head nod if you're okay with that so far. Awesome. Now, if we can fit these things to this thing to this thing, and then subtract them, we'll be just fine. So check this out. This is kind of interesting. So if I do, oh, wait a minute. 1/2 e to the x minus 1/2 e to the negative x well, if I have one, look at that. Do you see that e to the x is just going to be this bunch of junk? So this is going to be 1/2 times 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus blah, 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 blah. Minus 1/2 times, here's our 1/2, here's our e to the negative x. You tell me, does this fit exactly what this is?
No.
What's our junk here? So negative x is what I'm plugging in. So if I plug in negative x, then I'm going to get 1. I'm going to get, please look carefully, if I'm plugging in negative x, I'm going to get minus x. Do you see what? I'm going to get plus x squared over 2 factorial. Do you see why I'm getting plus?
Yeah.
Because if I'm plugging in negative x, I go, okay, 1, 1. Negative x, cool. What's negative x squared? Positive x squared. Okay. What's my next one?
Negative x cubed over 3 factorial.
Negative x to the third is still negative x to the third. It's negative x to the third over 3 factorial plus blah, 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 blah. Are you sure you're okay with this? Now something really, really cool is going to happen when we do this. Check this out. Ignore the 1/2s for a second, because naturally if I'm subtracting something multiplied by 1/2, I can subtract the terms themselves and multiply by 1/2 later. Did you catch that? So watch. What's 1 minus 1?
0.
Those are gone. Do you see it?
Yep.
Now this would be x minus negative x, so that does not simplify because that's going to be x plus x. That would give us 2x. But what's this? Yeah, junk. X squared over 2 factorial minus x squared over 2 factorial.
0.
Do you see that every even power is gone? Every even power. So the squared, squared. The fourth with the fourth. Let's combine what's left over. In fact, if I just factor out my 1/2, we're doing some advanced algebra here, all kind of in our head. If I just factor out the 1/2, what I'm going to end up getting is, well, here's,
2x.
and here's, remember, minus and negative is a plus. We'd get 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial plus blah, 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 blah. Did you catch that? We did some advanced algebra here. We're distributing our negative and we're combining our like terms. Basically, we're factoring over 1/2. No problem. Our negative would distribute, and then we're combining like terms. If you get that, your 1s are gone. Your power 2s are gone. Your power 0s are gone. Power 2s are gone. Power 4s are gone. Every even power is gone. Your odd powers will get added together. X plus x, 2x. X third, 2x third. X fifth, that's 2x fifth. Now, when I distribute by 1/2, what happens? With this one, and that one, and that one, and so on, and so forth. So this becomes x plus x to the third over 3 factorial plus x to the 5th over 5 factorial, which makes a series. Oh, let's do this together. Where does it start? It starts at 0, goes to infinity. Tell me about my powers of x. What do I have? Odd powers. Remember, if I'm starting at 0, is this odd power going to be 2n minus 1 or 2n plus 1?
Plus 1.
Because I have to start at the 1. So yeah, you're right. X to the 2n plus 1 all over. Tell me what I get on my denominators.
2 plus 1
1 over 1
factorial.
factorial.
Beautiful. That's exactly right. So, f of x equals sinh x can be represented by this on, now look back, what Maclaurin series did we use to do our work with? E to the x. So look at the interval of convergence for e to the x.
All real numbers.
Therefore, if we used a Maclaurin series which has a convergence of negative infinity to infinity, then this series also has convergence of negative infinity to infinity. So when we get something that's not explicitly listed, we don't want to make this thing up on our own, okay? We don't want to start doing derivatives of this. It's crazy. We don't want to do that. We want to base it on something we know already. The definition is this. Well, that's 1/2 e to the x minus, oh, look at that. This is exactly what this is. This is just this stuff with a negative x plugged in everywhere. We get here, multiply by 1/2, no problem. Factor out the 1/2. distribute your negative, lots of stuff simplifies out, and we got a very simple series to work with where we already know the conversions. So when I say represented, that means that this series will give us this function for any number of x you plug in, and that's kind of cool. We have one more thing to do, and then we're going to be done. Okay, this is the last thing. This is going to blow some of your minds right now, okay? This is what I really wanted to get to today. Because it's so interesting, it's so cool, I want to lead you down this road here. And I want to consider this. Here's my question. Do the integral. That wasn't a question, was it? Do the integral. Can you do it?
Yes. We use it.
How do you do it?
We use it.
Use some negative x squared.
Do the integral.
Do the integral. Can you do the integral? Is a u sub going to work?
No.
No, heck no. It's not a definite integral, so I'm not going from anywhere to anywhere. Can I do the integral itself? Oh, yeah. Here's how. Firstly, well, you know that e to the x, we actually just worked with it. 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus blah, 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 right? Hey, can you make this thing look like that thing? What's your junk here? So plug in your junk. If you plug in your junk, I still have 1. Then I have,
Minus 2x squared.
no, not minus 2x squared.
Oh, minus squared.
It's going to be a minus. It's just going to be x squared. Are you with me on this? Here's our x, right? Take this. That is now your x. Does that make sense to you? This is your junk. Plus we'd have negative x squared over 2 factorial plus negative x squared cubed over 3 factorial plus blah, 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 blah. Well, that's 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus what would the next one be? Come on, go for it. Are you with me on that one?
Yep.
Are you sure you're with me? Let's write this as a series. Our series would be 0 to infinity. Tell me something about our series. What would we get? Say what? Definitely alternating. And starting positive, so negative 1 to the n. We'd have x to the, tell me something about our x's. What's going on?
They're all even.
All evens. That would be 2n. No pluses, no minuses, just 2n. When we plugged in 0, we'd get out 1. We plugged in 1, we'd get out 2. All over what? That's right, n factorial. That's brilliant. Exactly right. Show of hands feel okay with this so far. You're sure you're okay on getting from here, actually from doing the x to the negative x squared. Do you see where that's coming from? We're just taking negative x squared and plugging it in every single place we got it. Now, this is so cool. If we want to do the integral, well, let's just, since we know that, where'd my pen go? Since we know that this equals this, since we know that this equals, you believe that, right? And it converges for all real numbers. Since this converges all real numbers, this is for all real numbers. Well, if this equals this, and I want to find the integral, do you remember anything about calculus? You can integrate on both sides of an equation. Well, then all I need to do is integrate this side and integrate this side. Integrate this side and integrate this side. What that means is that if I do my integral, I could do it from here actually. I'd have x minus x cubed over 3 plus x to the 5th over 2 factorial times 5. Well, you know what? There's an easy way to do it. And I showed you this before. If I integrate this one, what's going to happen to my power? Remember doing the calculus on these things? So this is a series. -1 is still going to alternate. I'm going to have x to the 2. And what do you do with integrals? Do you add or do you subtract? I'm still going to have an n factorial. But I'm now going to divide by my 2n plus 1. You can't put them together. There's still an n factorial, but now you're just dividing by that new power. That's exactly what you would get if you did this term by term. Term by term would give you x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial. It would give you alternating still. Odd x's. You see the odd x's? Odd powers of x? 1, 3, 5, 7. No problem. It's giving you over odd numbers 1, 3, 5, 7 times your n factorial. 0, 1, 2, 3 factorial. So you can do integrals of functions that you could not do any other way besides this. Is that not interesting to you? Isn't that kind of cool? We've done an integral of this thing. That integral will be represented by this series. If I want to find the integral of whatever I want, it's going to be on this series from -infinity to infinity, because integrating series do not change the interval of convergence. We talked about that before.
Do we need plus c for that or no?
Yes. Yeah. I don't even know if I put it on my notes, but plus c. Plus c means you're completed. That's right. Did that one make sense to you? Are there any questions on this before we end? So you got this from here to here, right?
Yeah.
You got that if this thing equals this, I can integrate both sides. And if I integrate both sides, well, if I have a series, I can integrate the series. If I don't have the series, I can integrate term by term, and it's going to come up with exactly the same series. That's really cool, Michael.
Are we gonna have to do that in this class?
Yeah. Have fun. We just did.